you click the go live button here. Okay, all right, so the YouTube is also up. In terms of questions that come in, there are questions you can enter in questions on the Q&A for the folks that are attending the webinar, and we'll try and moderate those as best we can. We'll also try and watch the YouTube feed as well to make sure we can try and answer all the questions that come in. So we're excited to get a chance to do this today. Let me bring up a couple charts here, and I'll just do a quick intro about Limitless Space Institute, and then we'll just get started. All right, can everybody see my slides? Okay, cool. My name is Sonny White. I'm the Director of Advanced Research and Development here at Limitless Space Institute. And so, as I said, this is the Interstellar Initiative Grants midterm briefing. We'll be conducting this Tuesday and Wednesday from 8 o'clock till about 12 o'clock the first day, and then 8 o'clock to 1 o'clock on Wednesday. Our mission here at Limitless Space Institute, we're here to inspire and educate the next generation to travel beyond our solar system and to support the research and development of enabling technologies. Our pinnacle objective, right, our North Star, if you will, is to enable interstellar travel by the turn of the century. And so this is definitely no easy task. It's very challenging. When you talk about the objective of sending human beings to the outer solar system and maybe onto the stars, it's very different from anything that we're used to in terms of talking about space exploration. If we wanted to send human beings to Saturn in 200 days, that's an order of magnitude more difficult than it takes to send a payload from the surface of the Earth to low Earth orbit. And so chemical propulsion for something like that in those timeframes, it just won't close, the system won't close. And so this requires us to develop some new approaches in power and propulsion, sometimes based on known engineering and sometimes based on engineering we still have to figure out. And then even in the farthest case, maybe the frontiers of physics can find some opportunities for us to maybe have different means or mechanisms to input a force into a spacecraft. So at LSI, we're all about doing things, and so we're conducting research on multiple levels. We do research internally through our EagleWorks labs. We're currently funded by DARPA Defense Science Office, doing some basic research on trying to understand the Cassibry phenomena. We're trying to fabricate some very tiny customized Cassibry cavities. We sponsor research externally through this Interstellar Initiative grants, and this is what we're going to hear about today. We have 9 grant performers that are going to give us updates on all their fantastic work, covering things from beamed energy propulsion, relativistic solar sails, fusion propulsion, space drives, and wormholes. So a lot of exciting topics today. We also do R&D through collaborative relationships with the university partnerships. Currently, we're partnered with Texas A&M on some developing a compact nuclear reactor design. We also have student programs. We've commissioned a week-long course for this summer focused on interstellar studies. So you can go check our website for that. We'll post the ability to register for that class if you have interest in that. So very much doing a lot of stuff. We're partnering with a lot of people. This is a kind of this is what I call our NASCAR chart. This is the different entities that we've partnered with formally just in our short period of existence, and we have several more that are currently in work, and we hope to continue to grow this collaborative relationship with all these people that have this interest in this domain and trying to engage in this way. So this is our schedule for today. I'm just doing the quick welcome comments here, and then I'm going to get Tim Crain, our keynote speaker, to give us an update on the work that Intuitive Machines is doing in returning the United States to the surface of the moon. They've got some commercial lunar cargo activities that they have that he'll share with us. And then we'll get into the updates from the performers. And the form that this takes is we'll have a 40-minute talk from each one of the performers. I'll have a little timer that'll go off and give us an audible warning at about 3 minutes until, and then we'll switch into some facilitated Q&A for each performer. And then we'll have a short break after the first 2, and then we'll come back and do the second 2. And we'll finish up the day with some closing remarks and any questions that we need to loop back and catch. So Should be a good day. I'm looking forward to it. Thanks everybody for joining us here today. We'll try and do our best from the moderating perspective to catch most of your questions. But just keep in mind that the questions will be facilitated at the end of each talk as best as we can do. So let me stop sharing. And I think at this point, I want to turn it over to Tim Crain. Tim, I think I've got sharing enabled. So
there we go. Great. All right. Everybody able to see my lunar surface with a large foreground lander and a small background lander?
We got you, Tim. Looks good.
All right. Now for the second trick, did that give you the presentation mode or the full screen mode?
I think you need to change the monitor where the presentation is. So if you look at on the top of your banner where it says slideshow, I think that gives you the option to pick which monitor you send it to.
Well, I'm maybe throwing my computer off as I have 3 monitors and it's confused. How about that?
No, not yet. There we go. Now we got it.
Good deal. Well, thanks, Tony, for having me. I'm super excited to be here today. And I won't be able to catch everything tomorrow, but I plan to be here most of the day today and see some of the exciting work that Limitless Space has going on. We're not quite as ambitious in terms of distance, but we reach just as far for the resources that we have here at Intuitive Machines. What I'll talk to you today is a little bit about our company and our founders, our objectives, and then our Lunar Payload and Data Services program, which is our internal program for cislunar space commercialization. So we have a checkered past, starting out as a think tank originally, which I'll talk about in a minute. But for the past 3 years, Intuitive Machines has been really focusing on lunar economies. So the commercial lunar payload services contract coming out of NASA ushered in a new era of governments engaging with commercial companies to provide kind of a hands-off attempt to deliver goods and services in the cislunar environment. And this is really a progression of procurements that you've seen coming out of the government, beginning with transition to ULA, the contractor execution with USA of the space shuttle program, then commercial cargo to ISS. Now we have commercial crew to the International Space Station. And so this is the Science Mission Directorate reaching out and saying, hey, maybe we can enable more lunar science through an extension of this commercialization approach, where the government shares some of the risk with the vendors, the providers, but does so with the opportunity to make much more significant gains. I'll talk about what some of those gains look like in a little bit. But one of our co-founders is Cam Ghaffarian, who I'm sure you've all met. And you know, Cam would never be satisfied with the big, hairy, audacious goal of just the moon. So the fact of the matter is, once you develop the systems and the capabilities to begin exploring the moon, very serious thoughts of commercially developing the solar system become possible. Once we develop our lunar lander and material return capabilities, we'll have 90% of what we need to go begin exploring the asteroids with the same systems. Once you explore the asteroids, you now have 90% of the capability we need to go to the moons of Mars and the surface of Mars, but in a context of a commercial company. And that's the difference that we're looking at, and expanding the human presence and really doing it by taking all the great lessons learned, but doing it in a commercial public-private partnership type of a setup. We are a relatively small company. We have about 120 engineers, 60% of which have master's degrees, 24% have PhDs. We have a relatively high percentage of PhDs, and then a smattering of bachelor's degrees. So we began the company with mid-career and senior NASA leadership and engineering professionals. It's what we like to call a salt and pepper startup. So a little bit of gray in the hair as we got going. And we develop everything from full spacecraft systems. We see a few of them here. This is our Nova M spacecraft, which I'll talk about shortly. This is the Nova C lander. This is the Micronova hopper platform. We do our own operations. We have Nova Control, which has been fully built, instantiated, and commissioned here in Houston in our offices. We do additive manufacturing. We also have advanced composite manufacturing and machining capability in-house. And then we do full integrated testing of systems. This is our VR900 liquid oxygen, liquid methane engine on a mobile test stand. And we went from designing the mobile test stand and the engine to testing it in something less than 3 months. So we also believe in rapid pace development and engagement of our hardware and software. So we develop everything from the full mission systems, turnkey services to the moon, individual spacecraft, and then we also sell our systems if it makes a strategic sense for us. For example, the igniter for our VR900 engine, we've human rated as a fault tolerant ignition system, and that's something we sell as a product to the human landing system vendors. I'm fortunate to be one of the co-founders at Intuitive Machines, along with Cam Ghaffarian, who you guys are familiar with for Limitless, and then Steve Altimus, who's our president and CEO. Steve, early in his career, launched space shuttles as a flight director from the Kennedy Space Center. And then for over a decade, he was the director of engineering at the Johnson Space Center and really brought in an era of innovation and creativity, unlike what had been seen in the Houston area probably since the days of Apollo. He was visionary and or foolish enough to fund people with crazy ideas like adaptive navigation systems, which was one of my projects, and this little lab called the Eagle Works, which Sonny White was the director of. So Steve was visionary and a patron of ours, and he and I both around 2013, 2011 maybe, began to feel like the great engineering acumen that had been accumulated in the NASA workforce and culture wasn't being fully utilized. And if taken out into a commercial setting, we could attack some of the intractable engineering problems, not just in aerospace, but also in energy and medicine. For about 4 years then, from 2013 to 2017, Intuitive Machines was really a think tank. And we did some pretty exciting stuff, everything from automated intravenous catheter devices to high fidelity gas blowout modeling capabilities to training facilities for the medical and the aerospace field. But once the moon began to open back up as a commercial opportunity, we really began to focus back on that. And for the past 3 years, as I said, that's where our energy and our heart and soul have been. We do have partnerships with some of Cam's other companies. X Energy is in a joint venture with Intuitive Machines to develop nuclear space systems. So their reactor technology and our space acumen come together for proposals we've put in for nuclear thermal propulsion, which what Sonny's charts will show you is at the very bottom edge of the capability you need, would be the most rudimentary, crude form of propulsion we might consider for interstellar transportation. Nonetheless, pretty exciting to work with those guys on NTP concepts. Also, we partner with Axiom Space, and we're helping them develop their rendezvous system. So a lot of our core capability, our strengths lie in automated systems, software, modeling of space systems and the control of space systems. From that, you can build whole spacecraft, whole autonomous capabilities for the moon. Just a few faces. This is something I bring up now to show people, in part to pinch myself. 3 years ago, the leadership and management team was Steve and myself. We've been very fortunate to grow the team with people like Anna Ronalds, who's our director of operations, Steve Lobby, who was one of my mentors at JSC for over 32 years. People like Trent Martin, who has a varied career, including being the project director for the AMS on ISS. But really a capable and full leadership staff, helping us not just with the technical side of things, but with commercializing. We talk about commercializing the moon. You really have to get on your bike and pedal, because it can't just be NASA. If it's just NASA, it'll be a program that runs its course, but then there'll be other priorities in time. And so we have to take this opportunity to grow into other sectors. And NASA actually encourages this, by the way. Part of the Commercial Lunar Payload Services program, they state that eventually they want to not only not be the prime customer, they would prefer not even to be the majority customer of our systems, and to spread the transportation, communication, delivery system costs and maintenance across a commercial sector. So we're working hard on our side to make that dream come true. We do believe in the growing lunar economy. There are published works by several think tank space futurist groups. Two here in the United States lately have predicted that the space economy, the cislunar space economy, is as much as $3 trillion over the next 30 years. There's some publications coming out of China which indicate that you could be a $10 trillion per year industry in the next 3 decades. So as engineers, we find ourselves fortunate to be on the ground floor of what will truly be an exponential market, and the beginning of human exploration out into the solar system. So in my 15-year vision, I would love nothing more than to have an asteroid fuel depot where perhaps a Limitless Space Institute sponsored propulsion test project gets built, fueled, and shot out into the deep dark for the first time. Those are the kind of futures I envision beyond just taking science packages to the moon, which is our near-term primary activity. So a little bit about some of the systems we're developing. We have 2 missions on the books. I'll talk about that shortly. But the early missions fly the Nova C. So C for Roman numeral 100, because the vehicle was designed to take approximately 100 kilograms to the lunar surface. Depending on trajectory and location, that can be as low as 80 kilograms. It could go up as high as 150 kilograms. So there's some mission variability, but generally it's targeting a mean of 100 kilograms. And my date here is a little dated. Up until last week, we were targeting a November 2021 first launch of that system, but that has now slipped to January. So nonetheless, we're looking at 9 months to launching our first lunar lander. All of the propulsion systems, all the software, all the structures on that vehicle are custom Intuitive Machines designs. And then many of the computers, electronics, sensors are COTS products that we bring in and then integrate into the overall vehicle. The vehicle does have precision landing and hazard avoidance. On our second mission, we'll be able to land within 50 meters of the target on the lunar surface and avoid obstacles up to 10 centimeters or down to 10 centimeters in size, and with slopes of less than 5 degrees. Lots of lessons learned extracted from programs that we worked on with NASA in our previous careers as civil servants. When you go up from the Nova C, the next class vehicle we have is the Nova D, and that's basically 2 Nova C propulsion systems side by side on a new chassis. And depending on the tank size for that configuration, we can do between 500 and 1,600 kilograms to the lunar surface. That vehicle will be available in 2024, 2025. That's the class of vehicle that you need to begin landing these Viper and lunar transport vehicle rovers. So these kind of small mini car type rovers, that would be the vehicle to provide that. And then on the right, you see the Nova M. So the Nova D is actually built to maximize the capability of a Falcon 9 booster. The Nova M then is built to maximize the boost capability of a Falcon 9 Heavy. So we get thrown into a very high orbit and then complete the lunar capture, powered descent and landing on all of our systems using liquid oxygen, liquid methane, which has a great advantage for us. Most of our competitors use less energetic propulsion systems and take 30 to 60 days to spiral out to the moon. Whereas we have more of an Apollo-like 5 to 6 day direct transit to the lunar orbit. The Nova M, however, is built for the Falcon 9 Heavy, as I said. And what you see there is an early concept of a fission surface power system. So that's a configuration we would have with the Nova M taking a 4 to 5 metric ton fission reactor to the lunar surface. And that's something NASA has been very keen on in the past couple of years. We've written one proposal for that project, and the next phase of that comes up hopefully before the end of this fiscal year, but definitely by the end of this calendar year. So that's kind of where we go when we go big with our lander systems. We also go small with our lander systems. I met with a colleague of mine working on the MSL precision landing system that very successfully just landed a few months ago. Congratulations to the JPL team. But I was floored by the fact that they had a very sophisticated landing vision computer and set of cameras that were on the base of the rover that they used for exactly 15 seconds during entry, and then never used again, although they continued to carry that hardware around the lunar surface with them. So we developed the idea of the micronova, or the hopper, which you can see here, which basically you can just barely see this camera lens and baffle is the same as that camera lens and baffle. This is our precision landing navigation pod, and the Nova C, Nova D, Nova M all have 2 of these precision landing nav pods on them. Well, basically what our hopper is we've mated a propulsion system to that precision navigation pod. And the concept is that this will land attached to the Nova C or higher class Nova vehicle, perform its function for the mothership landing, and then it will detach and fly away and conduct science experiments kind of as a vacuum drone. So in some sense, it's very similar to the Mars helicopter. Of course, we couldn't build a helicopter for lunar operations because we're in a vacuum. So we developed a propulsive system. It's a 4-jet thrust configuration. We'll be flying the South Pole hopper, which will have a 1 kilogram science payload, November of 2022. And then we have a proposal in for the PRISM program with NASA to fly a suite of magnetometer instruments through a 3D investigation pass on the Reiner Gamma magnetic anomaly on the moon. We expect to hear about that. We partnered with Arizona State on that. Expect to hear about that here in just a matter of a couple of weeks. So excited to see if that works. But the idea is to create a science platform that can fit something between, carrying everything down with you on the main lander and having to have a rover. And there's some places like the permanent shadowed regions that a rover is just not as well equipped to investigate as, say, a free-flying hopper. Already mentioned we have our Nova control ready. We've begun training in there and testing our communications loop. Very excited to get that up and running with the big dishes, which brings me to our LTN. We have a lunar telemetry and tracking network, which is completely independent from the Deep Space Network. The Deep Space Network, run by NASA and JPL, is a world-class facility of dishes and tracking installations and expertise, but it's oversubscribed. It's already oversubscribed for NASA missions. And with the growth, not just of our missions going to the moon, but with our competitors' missions and a growing cislunar economy, we felt that it wouldn't be prudent to rely on a currently oversubscribed government system as our backbone for communications. And let's face it, when you're talking about commercial missions to the moon, most of the value of what you're doing is the data that you bring back from your experiments and your flight telemetry. So we've gone through and we actually have contracted 6 dishes. This shows 4 of the main ones in Moorhead, Kentucky, Goonhilly, UK, Baialu in India, and then Parks in Australia. We've since added a dish in South Africa and are working on a dish in South America and another one in Japan. The idea is for us to have high bandwidth continuous communications with both our ground and orbiting assets at the moon at all times. We are in a field of competitors. So just to give a nod to other things that are going outside of Intuitive Machines, the commercial lunar payload services, the CLIPS program within NASA, have awarded 6 contracts to 4 different providers. We have won 2 of those contracts. One is for our very first mission, IM-1, flying to a mid-latitude location this January. The other one was to fly the Prime 1 drill, which will be the first water ice drill demonstration on the moon. We'll be flying that in November of 2022. However, Astrobotics, one of our competitors, also won an early contract to deliver about 100 kilograms in probably the first quarter or second quarter of 22. They have also a what they call their Griffin landers, what we would call our Nova D. They're on contract to deliver the Viper rover to the lunar South Pole in 23. Mass and Space Systems has a experimental lander where they're delivering about 6 payloads to the lunar South Pole late in 22, so after we've gone there. And then Firefly Aerospace was just awarded another of the contracts to a mid-latitude landing site. Both of those last 2, we were not sore losers, but disappointed that we lost them. We scored very highly technically, but the agency decided to spread some of the technical capability around, and we think there's a real desire on their part to get a number of competitors a chance to take shots at the moon and see who'll be successful. But there are other companies, we're in good company in the CLIPS program that have competed against us and have not yet won. So you'll recognize many of those names. And it's our hope that we can corner the market to some extent moving forward based on successes in our first 2 missions. So just to give you kind of a feel, we're shooting for an annual cadence of missions to the moon. The first mission, cleverly named IM-1, takes the first NASA-provided lunar payloads, the CLIPS payloads, along with 5 commercial smaller payloads that we've taken, not from NASA, and that will land at a mid-latitude site. That mission, we actually purchased a portion of the Falcon 9 booster capability. So we didn't purchase the full impulse that one can get from a Falcon 9. And what that means is we actually do a high geo transfer orbit and then a TLI, a partial TLI burn at Earth, and then we're off on our way to the moon. So that one adds about a day to our trajectory to the moon. However, beginning with IM-2, all of our Nova C missions, we will fully purchase the Falcon 9 booster impulse capability. And what that allows us to do is we can carry, in addition to our 100 to 150 kilograms of payload to the lunar surface, another 1,200 kilograms of payload that's unusable by the Nova C. Nonetheless, the booster can throw into a TLI orbit. And so we're marketing an ESPA ring below our vehicle to take up to 5 ESPA mounted experiments, spacecraft, ComSats, whatever the customers may need, as a ride share to get that high energy injection. If they want to go to the moon, they'll have to complete their own LOI because they're not connected to our lander. But they do get thrown into a 380,000 kilometer apogee orbit. So we're scheduling IM-3. We're very close to announcing that in late 2023. We're excited for that. As I mentioned, we could have Nova D as early as 2024. You might ask, if you can build a 500 kilogram lander, why did you ever build a 100 kilogram lander? We were surveying the market, and for the first few missions, 100 kilograms is about the sweet spot of the payload distributions that we need. But we are beginning to get our first inquiries about customers interested in 2, 3, 500 kilogram payload capacity. So that could be as early as 24. Then we could be doing Nova M style multiple metric ton payloads as early as 2026. Oh yeah, that's our ride share capability. So we're setting up in our LPDS program. That's a lot of acronyms I've thrown your way. CLIPS is the NASA program for commercial lunar payload services. But since we serve other customers other than NASA, we've set up internal to IM our lunar payload and data services program. And that services NASA's CLIPS, as well as pursues and works to establish the cislunar ecosystem of commerce that we're so excited to see. But we will be the first commercial lunar lander on the moon. We'll be the first lander to the South Pole, the first to drill for water ice at the South Pole, and with our hopper, the first to explore a PSR crater. We'll hop off the lander. We'll check our systems. We'll hop into the dark. There's some debate about whether we actually go down and land in that crater, or if we'll get down close to the bottom and hop out and beam our findings back to the mothership. It does get me excited to see the incredible work you guys are doing. And as chief technologist, I have to ask myself, what might we do together? And so the shameless plug and the thing that Sonny and I get together and whiteboard about, not as frequently as we would like, are what might you need that intuitive machines could carry on our platforms to the moon, to the asteroids, to deep space. And we'd be interested in collaborating with you on proposals, on preliminary concepts. We've worked with Phil Lubin on a couple of projects, so glad to see Phil here today, and have some ideas that fit within his research area. But yeah, as chief technologist, I'd be open to a conversation with any and all of you if you've got some ideas, and we'll explore them and tug on them and see if we can find an intersection of what our systems could provide with your ingenuity and experimentalist needs to really push back the darkness. And that's all I had today, Sonny.
Hey, thanks, Tim. Thanks for the outstanding presentation. Really appreciate you sharing some of the things that Intuitive Machines is up to. It's very exciting to see that. And I love the last little slide there, right? Kind of saluting the mentality of crawl, walk, run, right? We definitely want to try and be bold and lean forward, but it's always good to try and connect the dots and figure out, if we want to get to this point, and we're working hard to get there, what are some discretizations that we can determine along the way? And I think that's very effective to try and keep that thought process in mind. And so that's something that's definitely on my mind on a pretty regular basis. So again, thank you, Tim, for joining us this morning. It was really nice to have you. I always enjoy seeing your slides. And yes, we don't get a chance to get together and whiteboard as much as I would like to. So hopefully we can remedy that at some point in the future. But and maybe there could be additional opportunities for things that we could do, some early precursors as we continue to foster this early low TRL type of work. So let's go ahead and switch gears now. Get started with hearing from our performers today. We've got 4 speakers up today. First up is Jason Cassibry from University of Alabama, Huntsville. The title of his project is Exploration of Pulsed Breakeven Fusion at 100 kilojoule energy for breakthrough propulsion. And so Jason's going to go ahead and get started, and Jason, just to remind you, you'll hear a little alarm at 37 minutes just to remind you and let you know we're closing in. So
okay.
With that, you have the con, sir.
Great. Can everybody see the slides okay? All right, great. So thank you, Sonny, for the introduction. So my name is Jason Cassibry, and today I'm presenting our midterm briefing on our work with Limitless Space Institute. I'd like to acknowledge the Limitless Space Institute and the Interstellar Initiative grant for generously supporting this effort. So just to remind everyone, the objectives of our program were to develop a neutron scaling laws for fusion targets for pulsed Z-pinch fusion based on rising currents. Design targets to achieve tailorable ion densities near 10 to the 26 to 10 to the 28, pardon the lack of formatting there, meters cubed at peak current, and achieve validated simulations in our 3D SPF Max tool against experimental data and determine scaling laws and target variations to achieve ignition at sub-megajoule energies. Now, the reason for this is because break-even fusion, which I think most people agree would be very, very useful for the world if we were to achieve it, requires enormous energies and enormous powers. And with later technologies, emerging technologies, the size of the reactors that people are considering are starting to shrink down. In pulsed power, right now, break-even class fusion systems are around 50 to 100 megajoules. And if you've ever seen say, for example, 10 kilojoule capacitor, if you have to get to 50 megajoules, it's tons, literally tons and tons of large-scale capacitors. So it's very expensive. And if we can do something at the sub-megajoule level, we can greatly shrink that down for pulsed systems, which is what we're trying to do here. So the milestones of our program include demonstrate an inert target shot with successfully triggering framing camera, optical emission, and power diagnostics. So we did successfully get that going back in January. By March, we were hoping to have demonstration of lithium deuteride fuse targets and confirm neutron yield with time of flight neutron spectroscopy. We did spend extra time than we initially planned on developing a neutron shield and triggering and protecting the diagnostics. We did a lot of practice tests on a much smaller machine first in order to try to protect the diagnostics. So we're going to be working more on that here in May and June as we ramp up and start doing validation against our numerical model, in which we'll start conducting neutron yield scaling laws as a function of target mass and charging voltage. And then we will proceed with 3D modeling validation and development of scaling beyond the scope of the I-squared study, and then we'll complete mission analysis for outer planetary and interstellar precursor and interstellar flyby missions. I'll spare you going through the schedule. I just kind of put that up there. The team includes myself, Dr. Gabe Shue, and Mr. Sumantro Sinha, Mr. Alan Davis, Mr. Andrew Walton, and Mr. Jacob Kinsey. I meant to put him on there. I didn't get that in there yet. So our facilities consist primarily, our main system is Sparky. This is a 60 kilojoule pulse power system on wheels. We don't drive it around very often, but once in a while we might take it out for a spin. But anyway, this consists of 6 40 kilovolt capacitors, which dumps into a transmission line, and it's usually off over to the left somewhere. A lot of the hardware that you see up here are lines run for different diagnostics, for charging, dumping, firing. And then up here on the top of the machine, you see a rail gap switch, which basically closes the circuit, and that is triggered externally. So this is just a schematic of the diagnostic layout for the system. So let's take a look at the middle where we have something that is stated as a radiation shield. So this is kind of this rectangle here. These lines coming out are just to indicate that it would produce X-rays and neutrons. We have an oscilloscope and a digital delay generator, which pick up BDOT probes, which are on the transmission line for Sparky. Mark's trigger over here is what initiates and closes the circuit for the rail gap. And we have controller relays and power supplies, which kind of feed in over here. Our plasma spectroscopy looks through our mirror at the machine, so we don't have a direct line of sight to damage the camera. And then over here on the left, you'll see we have scintillator probes, and they're purposely set a few feet apart from each other, and one of them is behind the other. And what that allows us to do is to discriminate the signal. So there's 2 types of signals that'll come out that these scintillator probes will pick up. They'll pick up X-ray and neutrons, because the crystals will fluoresce when they are hit by high-speed neutrons. And if you have them apart by a few feet, you can use time of flight of the traces which go off to the oscilloscopes to discern which is X-ray and which is neutron. And then with the neutrons in time of flight, you can tell, are these 2.4 MeV neutrons from DD fusion, or are they 14.1 MeV neutrons from side reactions of deuterium and tritium, which would get produced when you burn lithium deuteride, because the lithium will fuse with neutrons from the DD reactions and make tritium, and that tritium will get consumed very quickly in the shot. So let's take a look at some recent diagnostics in triggering an improvement here. On the left-hand side, first, we have our neutron shield, which we're kind of proud of here. These are actually stackable water bricks that we purchased, and they're actually filled with borax. So basically, laundry detergent is our main neutron shield. And the reason that it's a good shield is because with borax, the boron actually absorbs the neutrons, but it won't do a good job unless they're moderated. So all the hydrogen that's in borax, plus the water, which is the borax is dissolved into just to kind of densify it, moderate and slow down the neutrons. It's about a foot thick, which is roughly what you need. And then the boron actually absorbs the neutrons that would be produced. So we installed, once we made this shield, we installed with viewports and optical fixtures incorporated so that we could watch the experiment with our optical diagnostics. We built a marks bank in order to enable more reliable fire control on pulse power machines. We actually had a mechanical switch to fire the thing originally just to get started, just to have something, but that's obviously a terrible way to do it because it's very unreliable and hard to trigger your diagnostics off of a mechanical switch. And then on the right-hand side, high-speed cameras and radiation sensors are electromagnetically shielded, which is very, very important. They're put in Hoffman boxes, and if you don't do that, you risk ruining some very, very expensive equipment because the electromagnetic signatures, which are created when you fire Sparky, a 60 kilojoule machine, is like trying to protect instrumentations from an equivalent of about 3 or 4 shotgun shells going off at once, equivalent in electromagnetic energy. So it's a lot of energy bouncing around, and you have to work hard to protect it. So the sensors have been made and incorporated, and so now we're working to try to interpret them and make sense of them. We have the spectroscopy for getting plasma temperature and also plasma density. We have high-speed imagery with our camera, which we procured last fall and got running over winter. Our time of flight simulator probes are the signals come into this laptop over here, and then the BDOT current sensing is produced over here. I'm sorry, that image kind of got blurry when I sized it, and I'm just noticing that. But our BDOT probes are basically what give us the voltage and current traces from Sparky. This is a spectrum to allow us to make an estimate of temperature. I think right now we're just getting a few EV, nothing remarkable in these pilot shots that we've been doing as we get all the instrumentation up and running. But the camera successfully, we triggered the camera successfully upon firing the machine. The snapshot missed the measurement of the peak of the deuterium ionization wavelength, so we're working to try to get that synced up better. We determined this because the variation in the transmission line spacing caused an unpredictable increase in inductance, throttling the current input. And so we've been working to try to improve our transmission line, which actually has been destroyed every shot. So we're working to improve that as well. Variation in transmission line spacing caused by the shock of the shot, delaminating the dielectric in the conductor. So here are some targets that we have actually attempted. These are very, very simple. We're just trying to learn how to manage solid state targets. The material that we use, lithium deuteride, is not a very good structural material. It's a great nuclear fuel, but in order to try to make better structures for it, we're just starting with basically putting powder on these 3D printed substrates and then closing the circuit across this gap right there. And then here we've just experimented with tape to try to temporarily keep the material from blasting out. And then it is dropped down into this container here, which is inside the shield. So here is an example of an image captured. I know that we need something in here to give a sense of scale, but this is roughly of the order of about a 1 centimeter across here. The higher resolution image captured the target evolution. The image shows the initial plasma forming upon firing, and additional focal lenses are being installed to allow simultaneous measurement of temperature and plasma image so that we can gain a better insight into the implosion velocity and temperature. So here is just a shot of Sparky firing in open air just to kind of get a sense of what it's like. Let me just play this video for you real quick. So when it goes off, you do have to wear ear protection because it's very, very loud. So here it is with the lights back on and everything turned off. So we have a couple of people over here. I believe that's Jacob Kinsey working in the lab coat over there, and that's Sumantro area. So the main improvement areas to mention today, strengthening the transmission line to allow them to survive more than one shot, better characterization of target transmission line impedance to allow better tuning of trigger timing for cameras and radiation sensors, and better control of fuel mass addition when fabricating the targets to ensure current flow through the fuel instead of bypassing it through the air or dielectric. So let's go ahead and shift gears. So one of the things that we promised to do was mission analysis. And I think we're going to be going full steam ahead later in the summer on experiments, as we're about to move our lab, actually. So I thought I would front load stuff that we said we'd do later and do some of the mission analysis now. So on the left-hand side, this kind of just frames what missions are possible with the known physics that we have. I'm really hoping that some of these propellantless concepts take off, no pun intended, and allow us to get away from the tyranny of the rocket equation. But until that time, this is what we have: throwing gas out of a nozzle and possibly laser light craft. So these are the primary ways that we have propulsion, and their performance is really based on the energy density that's possible by the fuel that's stored. And then I figured out a way to get light craft on here because I wanted to acknowledge the exciting capability that Phil Lubin's concept can also deliver. So on the x-axis, you have energy density, chemical, and then there's this big gap, and then you can get up to about 10 to the 14 joules per kilogram in nuclear, both fission and fusion. And then about 100 times better than that is antimatter. And then a little bit beyond that, because all of your energy is stored in a station off of the vehicle, you have something like laser light craft. And that kind of gives you an estimate of what delta V's are possible given these different scenarios. These horizontal lines give you missions that get progressively harder. So for chemical, you could do a lunar round trip in a week, a Mars round trip in a couple of years. But if you push up here to say a Mars round trip in 6 months, you can't do that with chemical. The vehicle is just prohibitively heavy. It's just not really possible unless the engineers think of something much more clever that I can't imagine yet. But with nuclear, you can do that. Nuclear thermal in 6 months might be a little bit of a stretch, but you could certainly do it with an advanced nuclear electric or fusion or a fission-fusion hybrid, perhaps. Do the Mars round trip in about 6 months. A Titan sample return, if you start to think about the science missions, could be done in a couple of years. Heliopause flyby in 5 years, so less than a decade. An OARC cloud flyby in about 20 years, and a gravitational lens rendezvous in 10 years. Then there's this big gap because I simply don't know what is out at these distances between the OARC cloud and our nearest star. Perhaps there's some things interesting out there. We just haven't found them yet. Now, over on the right here, we're flying through the solar system in the neighborhood of the nearest stars. The ones that are highlighted with red are the habitable planets that are nearby. But just to kind of conclude on this particular slide, so chemical propulsion is great for launching cislunar space, and it's kind of marginal for Mars missions, although we can do it. Fusion propulsion, fission-fusion hybrids in nature, and really they enable just about all interplanetary missions within a decade, and journeys out to the OARC cloud within 2 decades are possible. It's kind of marginal, a fusion is, for interstellar missions. It can be done within the lifetime of a human. Antimatter and laser light craft really are kind of what you want to push towards, or maybe a combination of those, and then a fusion or a nuclear system once you get into the region of the destination planet so that you can maneuver within that solar system. There's no one magic propulsion system for everything at the moment, so we have to use a combination of things. But as we kind of think of what to travel to, you take a look at the celestial neighborhood here on the left-hand side. This is about the extent that humans have traveled, out to about 3,000ths the distance from the Earth to the sun. So just barely scratched the surface. Most of our interplanetary missions, I think 90% of them have gone to just Mars or Jupiter or within the inner solar system. So very few missions have gone to the outer planets, or certainly nothing interstellar yet. And it's simply because it's really hard, which is one of the reasons for this interstellar initiative, is to try to enable better propulsion systems to do these things more rapidly within the solar system to make them more practical and enable new and exciting missions that we just can't do right now. And there are lots and lots of places to consider. These are terrestrial worlds sorted by gravity. And you can see there are lots and lots of rocky planets and dwarf planets. Most of them have of the order of a few percent to 10% the gravity of Earth. Most of them are cold. So if you develop a system that can get within the solar system fairly quickly, you can use a lot of the same technology to explore many of these things. Our interstellar neighborhood, when we start to look at that, there's several places that we can go. Proxima Centauri b, Wolf 1061c, Gliese 667c, and GJ 357d. I'm sure there are others that are nearby. We just haven't found them yet. So these are all within, say, 30 light years, with Proxima Centauri being the closest one. And then as we turn to fusion to look at some of the missions that are possible, there's an enormous wealth of previous knowledge that has been developed on these different concepts. So we certainly don't want to forget about those, and we want to try to leverage all the ones that have been done. In the interest of time, I'm going to kind of gloss over this, but this is a TRL traversal, which we've interpreted for fusion, and you could borrow this in order to change it for some of the other advanced concepts out there. But basically, TRL1 is your back of the envelope estimations. And then somewhere in the middle, you have proof of concept and breadboard. And then at 5, TRL5 ground test with flight weight components. And then you gradually develop the space flight system and you do your first demos. Your first science mission might be at TRL8. A first human piloted mission would be 9. And then routine usage is 10. As we think about doing missions, you got to figure out how much it costs. And for science missions, it makes sense to just kind of leverage the data that has been generated in terms of the cost of those missions. And so there's when I first saw the citation for this came from Saroj Kumar, one of my grad students, who's not on this, he's on a different project. And I said, where did you get this? And he cited the source. And I went and I couldn't find it. And I asked him about it. And he said, well, you have to go pull out all the data from the individual missions. So he really did himself a disservice by not explaining all the hard work that Saroj did in coming up with this chart. But it's roughly a straight line through that. And you could almost consider this a design goal. Your mission ought to cost something within this a trend line through this data, if you can do that. Now, why we think fusion or pulse fusion in our case can do these kinds of missions and achieve it on a smaller energy compared to some of the things that have been considered is simply because of the power balance studies that we've done, like this one. And what we're seeing here, this is kind of a busy chart, but it's density of the plasma versus temperature. And this is a power balance, which kind of shows if it's blue, it's cooling off. If it's orange or green, it's heating up. So you want to be in this space. So you want a plasma that's imploding and basically goes along the line until it gets up into the ignition temperature regime. Then you want it to burn. Tokamaks are way over here on the left. Laser fusion is way over here on the right, around 10 to the 31, 10 to the 32. And basically, we want to climb this hill just to the left of this blue border here. Over here on the right-hand side, this shows you the energy of the plasma for a 2 millimeter scale plasma. And so right in here, you have the sub-kilojoule range, which is what we're going to try to get to, not with Sparky because it's not powerful enough, but with systems that are derived from Sparky. Our simulation tool, SPF Max, it took several years to get the hydrodynamics and plasma physics working properly. It took me about 8 or 9 years to get the electromagnetic field model to work in the way that we want it to work, which is to basically treat the plasma as a circuit. So it actually just started to become reliable this spring as we've kind of worked through all the issues. We'll be hopefully getting this work published soon. But on the right-hand side, this is an animation of a Z-pinch that we did recently. And the implosion rate, not necessarily on this particular case, but on another one that we just did, is within about 10% of an exact solution. So we're really excited that it's starting to get the coupling between the external circuit and the plasma down accurately. On the left-hand side, this is just a notional magnetic nozzle. and we're working towards doing some new simulations with that. As we look at some of the missions, some of the harder ones that would really exclude most propulsion systems, at least the conventional existing things, something like a rendezvous with the dwarf planet Eris. So here with a 1 kilowatt per kilogram system, you could take a 20 metric ton payload out to Eris and rendezvous with Eris on a time frame of about 8 years. The total vehicle is about 40 metric tons. It requires 68 newtons of thrust and ISP of 25,000 seconds. Rendezvous with a gravitational lensing experiment. This would actually require an advancement in technology to a 5 kilowatt per kilogram system. So you could either use the same technologies but get better at burn physics and have a higher yield per shot if this is a pulse system, or you'd have to make significant advancements in capacitor technology. But you could do this in about 15 years with a system like this. You need about 110 newtons of thrust and an ISP of 77,000 seconds. And there's about 41 megawatts of jet power. So this is my final slide, and then we'll open it up for questions. So fusion concepts enable rapid interplanetary spaceflight for human piloted and science missions and interstellar experiments will explore neutron universe peak current, relying on Z pinches during the first quarter period. Diagnostics include fast framing neutron scintillator probes, BDART probes, spectral intensity, and broadening. They have all been successfully triggered while being protected from Sparky, which was not a trivial exercise. And SPF Max has successfully been coupled with an external circuit model, so verification and validation are now underway. And with that, I will yield the floor back to Sunny and the general audience, and happy to take your questions. Thank you.
Hey, thank you, Jason. Great presentation. You actually didn't get the red alert sign, so very good. Monitoring the time, man. Fantastic.
I'll try harder next time.
So, well, Phil's up next, so I know Phil. He'll probably get the red alert. So, thank you for the presentation. Certainly enjoyed it. I think we got a couple of questions already in the Q&A, and let me remind all the folks that are watching on the Zoom webinar, just type your questions in the Q&A panel. If you put them in the chat, we'll try and port them over, but Q&A is what makes it easiest for us. And for the folks that are on YouTube, we'll try and also moderate questions there. So I got a question from Scott Shu, and he's got two comments here. I'm just going to go ahead and read them both. So Scott asks, maybe I missed it, but what is the actual fusion configuration? I think he's trying to figure out, like, you've got your targets that you were showing us and so forth. How does this kind of map to some type of embodiment, if you will? How does that's connected to the hip bone, right?
Yeah, absolutely. I would say this is, so we didn't really illustrate it clearly in this talk today. Scott, thanks for the question. But notionally, what we would have in mind is something like a Z-pinch, and it's imploded by an external liner. So it's sort of a 1-2 punch. A Z-pinch, it's not too hard to get the temperatures up to a couple of hundred EV, and it'll stay stable as long as the current is rising. So what you want to do is find a pulse shape that gives you a stable current and have it rising up to the point just before the current reaches a peak, and size it with a few mega amps of current to get a few hundred EV temperature. And with that, if you then implode it with a surrounding cylindrical liner, you can get it into fusion relevant temperatures, or at least that's kind of the thinking. Now, the problem with this is that when you get into the blast from such an event, it's going to be hard to get the plasma facing components to survive that shot. But what we're trying to do is to come up with something controllable and worry about the destructive part of it later. We're just trying to see, can these conditions actually work? We're not going to get there with this particular program, but we think that we can at least start doing some of the simulations this summer to see if it's even practical or not, and if there's a scalability. But obviously, longer term, if this works, then that at least gives us kind of a frame of reference for, okay, now how can we do this in a way that's non-destructive to the driving components?
Thanks, Jason. If you could you stop sharing? That way we can get everyone's can see the speakers. So, thank you, Jason. Got another question from John Scott. How does your nozzle get the ISP as low as 11,000 seconds?
It's well, a really bad nozzle will just give you terrible ISP, so that's the easy part. No, but seriously, what you do is you have to mix a burning plasma with an inert propellant in order to get the ISP to slow down. How you design the nozzle is very much an open question. We recently developed a relationship with some cohorts in Japan who have actually done quite a bit of multidimensional modeling with the PIC code, and they've done some low energy scaled experiments, and this has all been motivated by Vista. But we kind of think that the magnetic nozzle topology would probably be a combination of solenoid and longitudinal windings, kind of like a diverter yoke on an old television set that we're all throwing away. But the ISP itself, to get it to that, you generally have to mix it with inert propellant to slow the plasma down. Great question.
Thanks, Jason. Let me also open it up to the panelists here. If anyone on the panelists has any questions, feel free to chime in.
Go ahead.
Jason, great talk, thanks. I had a quick question about your Z-pinch concept and for propulsion. What kind of repetition rate are you considering for your propulsion, and how do you achieve that? Yeah.
So nursery for propulsion system, I think you're looking at about 1 hertz, give or take, in order of magnitude. Whether or not you can reparate it that fast, I believe there's a facility at NRL that's comparable to what we would want to get to that already does about 5 hertz. So the ability of a pulse power system to do that exists. But then how you do this in an environment where you've got hundreds of megajoules of yield with each shot, I gotta say I don't have a good answer for that yet. So that's something that we're still exploring.
Thanks, Jason. We got a question from Jerry Sanders asking, is there a minimum size or engine/mission scale for this concept? What's the entry point type of thing?
Yeah. So I think that about as small as you can get with a fusion system, total energy storage with a pulse system is probably going to be a few to 10 megajoules of stored energy, maybe something slightly smaller. It's really hard to get a flame kernel to work in fusion. When you kind of work out the math, if you have a lighter and you spark it, the spark mixes with butane and oxygen, and those sparks, there have to be enough of them in order to heat the surrounding fuel to get it to burn. In fusion, it's a real pain in the rear because the products come out so fast that they don't deposit their energy locally. So you have to have enough of those products being produced to heat the surrounding cold fuel that's immersed in it in order to get it to burn. And with a few Tesla, you can get away with about a megajoule in the plasma and get it to burn. You have to really crank up the field high in order to get it down into the sub kilojoule range. And then that adds other complexity. So it's just really, really hard to get it a lot smaller. Aside from the pulse systems, the steady state devices like tokamaks, it'll be really interesting to see how these magnetically confined systems can shrink down as those technologies, the superconducting ribbons get more powerful and things get smaller. So they might in the long term, lead to more practical steady state devices. But for pulse systems, it's looking like a few megajoules is probably the minimum size. Kelvin had a question: what software are we using for your mission analysis? I'm just using straight line trajectory calculations from the author, I think, was Wolfgang Mokel, and the paper came out in '72, and I can send you a link for that, or my lecture notes that I make students learn it on. So I can send that to you.
Did you describe the capsule designs at all? What sort of masses would have been involved in the pulse units that you drop into the target chamber?
No, we haven't really described that yet, simply because we haven't done the scaling laws yet to kind of figure out what size targets we need.
Are you looking at sort of NIF type size? Is that what you think?
Yeah. Notionally, it would be something of that scale. Maybe that size, but probably a little bit smaller, I think.
Yeah, I mean, why you talk about 1 hertz pulse frequencies? I mean, that's really low. I mean, even NIF might have gone up if it was successful. Ignition could have gone up to, in theory, 10 hertz at some point. I mean,
oh sure, yeah. If you can get to higher pulse frequencies, it just sounds hard. Given how hard it is for us to fire Sparky, it'll be really challenging. But yeah, certainly, if you can go to higher pulse frequencies, you get higher throughput, higher thrust, all that. Yeah.
So is 1 hertz then just kind of your best guesstimate based on some modest extrapolation in your mind?
Mm-hmm. Yeah, that's how quickly we think the space gnomes can replace all the hardware after each shot for the next one.
Right. Got another question from Scott Shue. He asks a comment and then a question. You might get the Z pinch to stay stable long enough for the preheating phase to several hundred electron volts. Mm-hmm. But how do you get the Z pinch to stay stable for long enough through the liner compression?
That is a very good question, and it's something that we're going to explore this summer when we do scaling simulations to kind of see what sort of problems are going to creep up on us. It's not something I have a good handle on at the moment, for sure.
Just another comment quickly on the pulse frequency thing. I understand your conservatism, but I mean, the thing to keep in mind is that capsule implosions, I mean, the hydrodynamics will happen in sort of microsecond timescales. The thermonuclear happens of the order nanoseconds. So you're talking about, a millionth from a billionth of a second. So you've still got a lot of time to play for. It's difficult for us to intuit, but it's a lot of time to play for in that 1 hertz, a whole second. You could fire a lot of capsules in principle. So I think there's a lot of room there. I think the thing that bounds it to me is the relaxation time of, if your plasma is expanding into a chamber or into an nozzle, and how long that takes to rebound, and that potentially is what will slow the whole process down.
Mm-hmm. That's a good point. I think your time scales that are hard on for all of this are the evacuation time out of the nozzle and the pulse recharge time of the capacitor bank. But I think it's the former one that probably might be limiting if you can have good cooling on your reactor.
Good question. Good question, Kelvin. Good discussion, Jason. I'll finish with this one question. Jason, can you just kind of give me, what got you into fusion? What's your history in fusion? Why fusion?
So when I was in high school, it was actually my grandmother's best friend, Linda, came over. I was over at her place, and she brought over this Discover magazine that had an article on fusion. And I was already thinking aerospace propulsion. Both my grandparents, my grandfathers were pilots. I had an uncle who was an aerospace engineer. So, aircraft and space were just kind of in my blood. But this article talked about how fusion could open up the solar system. And that captured me. And in a very stubborn way, I just could not let that go. And it took until I was working on my master's degree up at Illinois that I met George Miley, and I got an introduction to fusion in the late 90s. And then that led to me coming down to NASA Marshall and working at Huntsville, and then the rest is history. So when I first was interested and tried to look into it, this really dates me, but this was before the internet, kids. This is before the web was invented. My junior year of college, basically, when it became practical, and you couldn't Google anything yet.
Yeah, that's awesome. Thank you, Jason. Really appreciate your presentation, and thank you for answering the questions. I think we'll go ahead and get a little bit of a jump start on Professor Phil Lubin's talk. I know Phil has always all kinds of incredible stuff to share with us, so I want to give him a few extra minutes, if you will. Phil's going to talk to us about his work with directed energy for revolutionary space propulsion and power projection. Most folks know Phil, but in case you don't, he's a professor at University of California, Santa Barbara. Phil, I'm going to hand the microphone over to you. And you may have missed this morning, I have a little timer that'll go off with an audible alarm at 37 minutes with a red alert sound from Star Trek. So you'll hear that in the background. That'll be the audible cue to let you know you have 3 minutes. So, and that was based on your guys' request that you wanted the red alert sound. So
I love it.
You have the con, sir.
Thanks a lot, Sonny. Yeah, great discussion on fusion. I really enjoy this. Okay, well, thanks for coming online for everybody here. Let's see. I want to give you both a bit of a summary. We have a little more time for this talk. Last time was 20 minutes. This time we have 40. So I want to give a little background as well as our latest results, and kind of talk about really this program is a road mapping program. It's not a single element program, and there's many off ramps to this roadmap, some of which were alluded to in Tim's talk about a variety of opportunities, relatively nearby. So I want to talk to you about that. Okay, if you're interested in our work, check out our website. We have, I think at last count, about 56 or 7 directed energy papers of our approximately 500 papers, which are mostly cosmology. You can look us up online. It's a lot of technical details in our SPIE and Optical Society papers for the technology of photonics as related to long-range power projection and propulsion. We have some recent new input. Our NASA Luster program, which is directed energy on the moon, was approved, and the program starts sometime next month. We also have a DoD program on power beaming that also should start next month. And then we have a program in negotiation with the Breakeven Foundation on communications with Breakeven initiatives for Starshot. There's a TED Talk out there interested in any of the popular discussion of how one can use directed energy for reaching relativistic speeds. And then there's a couple of new papers that are particularly relevant. We published one about 2 months ago in ACTA called Fast Solar System Transportation, particularly relevant in a discussion we'll have of how you really negotiate this roadmap from now until implementation, sort of ultimately a relativistic flight. But along the way, a lot of things you can do, including going rapidly to our solar system. So that's published, came out of an STRI NASA proposal that we put together. And there's a paper coming out on beam propagation simulations with large scale laser phased arrays. We figured out how to do 10 billion elements in simulation using GPUs. So rather clever technique. We introduce all the perturbations we know, including photonic noise and fibers, amplifiers, and system noise. Along with that, the circuit perturbations for ground-based systems. So this system can be either space-based or ground-based. To start with, it'd be ground-based, just because the costs obviously are vastly lower during the demo phase. Long-term implementation, my feeling is space-based for a variety of reasons. So that's coming out in OSA, Optical Society of America, Applied Optics, probably in the next couple of months. It's already been accepted and is in the press. Some recent papers. There's the OSA paper. Bunch of interesting papers, I think, on relativistic damage to spacecraft. One in February, APJ. Another one in JVIS this year. I've also been doing some work in neural networks for autonomous spacecraft. So, autonomous driving on the Earth is nice, but eventually you're going to want autonomous spacecraft. So we have some very clever students working on deepening using quasi-artificial intelligence, but neural networks in very small formats. So amazing what you can do, to be honest. I'm learning a lot from my students on that. Again, the fast solar system transportation, I think this is particularly interesting for this audience. Challenges of communication, colleagues David Messerschmidt and Ian Morrison were also part of the Starshot effort. And a recent paper that we published in the European Space Agency, which is kind of an extended version of the roadmap paper, but was done in 2020. This is, again, I think it'd be a nice overview if you want to come up to speed as to what we're doing. And the JBIZ paper in 2016, which was submitted in April, I think 2015. So we have kind of a long history here. This program starts actually in 2009 for some work that was looking at for terrestrial, the equivalent of planetary defense, but for terrestrial applications. And then we branched out immediately into propulsion. So it'd be neat, if we could go a lot faster. And the nice thing about direct energy is it's a very scalable technology. We can have direct energy systems literally fit in your hand. We'll talk a little bit about for the Luster program. And then you can have direct energy systems that are effectively infinite scalable. There's no upper limit to the power. It's a completely scalable technology. So this is an example of what we might do for a ground-based system. For example, like our NASA Starlight or the Breakthrough Starshot program, it would have a ground-based system, in this case shown in the Southern Hemisphere to Alpha Centauri. But it can also be used to drive ion engine missions rapidly in the solar system. One of our targets is discussed in the ACT paper, is getting to Mars in a month, including stopping, which is wise for people on board. And you don't have to have a DE system on Mars to stop. You can actually fly the ion engine and do it all from Earth or lunar directed energy systems. So this is a really interesting concept. It's kind of the equivalent of nuclear electric propulsion, except you leave your reactor at home and just beam the power up. If you want to go relativistic, using ion engines or any accelerator-based technology on board does not work because of the secondary mass that you have to carry along. And there you need to go to direct momentum transfer with the light. And that's the way to get to relativistic speeds, at least in the kind of system space. So you use direct photon matter momentum transfer reflectors. Better, you get a factor of 2 versus absorption. You wouldn't want to absorb it anyway, otherwise it'd be a very hot journey. There's a misconception here in particular about the relativistic missions. The laser is not on, the phased array is not on during the entire trajectory. It's only on for a very limited period of time. For small missions, kind of what we call wafer scale spacecraft missions, it's only on for a couple of minutes, and then you turn it off, and then it's a ballistic trajectory. It's like firing a gun, and then you go to the next one. I think it's really important. People look at things and say, this is going to be impossible. Well, some things are inconsistent with the laws of physics. This is not one of them. But I love this great quote from Arthur C. Clarke. The way to discover the limits of what is possible is to go into what people would consider to be impossible. So this is really important to understand what was considered to be once impossible and now is routine. Things like what we're doing today, if you go to Disneyland in 1960, you'd see the video phones that were being talked about. Of course, now we just take it for granted. Like, our world is a Zoom world now, but in 1960, that was considered to be something only a few have, and that really never took off anyway. I used to work up at the Rad Lab, the Berkeley Rad Lab, which is the Lawrence Berkeley Lab. This is a picture of Ernest Lawrence in 1932 with the first cyclotron, which is about the size of your laptop, a little bit bigger, but not a whole lot. And if you told Lawrence to build an accelerator that was the size of San Francisco or larger, obviously would say, well, that is not feasible. I don't know if it says impossible, but it's not feasible. Lawrence had passed away by the time I was there, but I knew many of the people who worked on first cyclotrons. And there was a steady evolution from cyclotron to Bevtron, on up to linear and then circular colliders. And now we have the so-called future circular collider, which is going to be 100 kilometers in circumference. So again, what seemed, quote, impossible in 1932, some roughly 90 years later, is just taken for granted. Yeah, of course you can do that. So I think we have to be very, very careful with the word impossible, because oftentimes the impossible turns out to be just routine. Okay, we've done a lot of work, as you may have seen from our previous presentations. I don't expect you to read any of this. There are some very new results that are just literally hot off the press. One of which is we've achieved complete bidirectionality in our system, which is critical. And we've, for many years, proposed our phasing solution, so-called phasing. How do you phase up all these elements in a phased array? Now we've actually proven it in the laboratory that we can do it, and we have data. We've had data for many years as we've discussed this, sort of incrementally, but now we've run at full power with a very high dynamic range between the phasing beacon coming in and the output power going out, and it works. So that was achieved a couple of weeks ago. So nothing new. We've been saying this for, gosh, I don't know, since 2013, I guess, in our first SPA papers, but now we have proof that it does work. So, okay, our research team's a lot of great people on our team. This is some of them, from research scientists, research faculty, project scientists, collaborators in various parts of the United States, a lot of them from the DoD community. Lincoln Lab is one of our major collaborators. We have a lot of students involved as well. This type of program works really well with undergraduates and graduate students. And some of the undergraduate progress is just frankly amazing. I knew next to nothing about neural networks. I had an undergraduate working with me on some applications. He told me about his interest in neural networks. I said, yeah, go for it. So he comes back. Now there's 3 papers, one published, one in press, and another one in the pipeline, probably one after. I am just blown away by the creativity of undergraduates. The undergraduates are also working on the lunar directed energy program, the NASA Luster program for putting DE-powered rovers on the moon. Okay, this is really a roadmap. I think if you don't appreciate that part, you really miss the core of the program. It is a stepping stone along the way. You start with something very small in the laboratory. First you start on paper, then you go into the laboratory, and then you kind of take your stuff and you prove it in the laboratory, which we've shown now works really well. And then you want to go outside and prove that you can, expand the aperture. The power actually comes relatively easily. That's just a polarization issue. But aperture baseline is a big issue here. And then you work your way kind of slowly up the ladder here, and there's applications along the entire way. There's technologies, there's new technologies that we and others are working on. There's the scaling of the size of the system. So, 0.01 meters is, a centimeter. You can have directed energy systems, which I'll show you some examples of later, where we beam power in our lab. The ones we'll put on the moon will be more in the 0.1 meter class. And you just work your way up. And by the time you get up to kilometer scale in aperture, you're now reaching the point where you can achieve relativistic flight. Between 1 and 10 kilometers is sort of the sweet spot for beginning relativistic flight. And there is no upper limit. You can build something like, one of my students was really into Star Wars, and I asked her one day, how big was the Death Star? So one of our programs is called DE-Star, which if you say it right, you'll figure it out. And she told me it was 900 kilometers. So she's a total Star Wars fan. So I figured, okay, we have some ways to go. With 900 kilometers, you could do a total kick butt job in terms of relativistic flight. But there's all kinds of applications along the way. There's a helicopter on Mars right now that flies more or less once a day. And what if you could use some of the nuclear RTG power on Perseverance and use that to beam it to a helicopter? You could, keep it up, more or less indefinitely. So, on Titan is another example, lots of other applications, point-to-point power beaming on the moon, all kinds of things we've been talking to people about, in particular with Intuitive. Okay, space debris mitigation, planetary defense applications. We have about 20 papers on that. And then I think that the solar system, not just solar system-wide power beaming, power projection across vast distances, but the ability to propel spacecraft in the solar system for specialized applications, such as getting humans to Mars rapidly, it actually becomes viable. And I'll show you a chart pretty soon about And then things like solar system-wide LiDAR systems for detecting small bodies that threaten Earth. It's sort of like the Chelyabinsk class system. Missions to Kuiper Belt, Oort cloud, obviously the lunar application space is a really good one. Rapid missions to Mars and small missions out to the deep solar system targets, all kinds of things. Station keeping, imagine you want to keep a spacecraft in orbit longer, you don't want to have to refuel with chemical propellants. This is another way to beam power up and run a high ISP ion engine. Okay, well, this is the way that we propel things in general. We're kind of down here with chemistry at the moment, works great and continue to do so. You can also use nuclear thermal, as has been done in the 1960s. Obviously, we made great progress there. A lot of stuff coming, as has been talked about this morning. You can work your way up into sort of direct exhaust, nuclear applications. You can do sort of an EP, nuclear to electrical, running a generator to an accelerator or an ion engine. Do the same thing with sunlight, which has been on a number of missions now, which this is for granted now. And then if you really want to get to ultra high speeds, both in the solar system and go relativistic, then directed energy is one of the ways that you should be considering. So this chart has not changed at all, really, since our first work started back in 2009. We've just been progressively picking off the tall poles along the way. It is a parallelization issue, much like you build a supercomputer, you just add a lot of CPUs to get more speed. In ours, we add a lot of optical amplifiers to get up to higher power levels and smaller beam size by spreading them out. So it is a completely parallel system. It's very much like a Fourier transform. You're able to phase shift and amplitude modulate the optical amplification speed, and then you combine in free space. And that combining in free space means there is no upper limit to break down the vacuum. And the vacuum breakdown is a flux issue, not a power issue. So there is no upper limit to the that you can achieve. It's a phase control algorithm issue, which has taken virtually all of our time to figure out. In our first concept, you have a reference beacon on the spacecraft and use that to phase up to, much like you do in adaptive optics and astronomy, where you use an artificial guide star, which is an incoherent source. We use a coherent source and we could actually measure the phase directly, use that phase control, phase measurement to control the phase shifters, and then you end up with the beam that you want on the target, including going through the atmosphere and dealing with the atmospheric perturbations, which that works. We've done this in our laboratory, simulated with the deformable mirror atmospheric perturbations from models we have of the atmosphere, and we're able to keep up with the perturbations. There's two modes of operation, as I showed. One is converting light to electricity and running an ion engine. That's what we call the indirect drive mode. We have had a NASA phase 2 in collaboration with JPL for that program. We've now 3 NASA NIAC phase 1s and 3 NASA NIAC phase 2s, so a total of 6 NASA programs so far, in addition to our private foundation work, such as the generous support from Limitless and Breakthrough Foundation and another foundation as well. It's been very generous stuff. Okay, anyway, so 2 modes. Direct drive is the photon momentum exchange for relativistic flight, and then indirect is to get rapidly with high mass missions in the solar system. The key here is that if you want to go relativistic, you want to go to low mass in general for the same size system or same power system. If you want to get 100 tons to Mars, this is not the way to do it. Don't use direct drive, but indirect drive, because you're not really interested in getting to relativistic speeds. Going to Mars, you're interested in getting there via an order months. Very important to understand the distinction here. SIC unit just used in 2 different applications. So it's nice, scalable, and in a variety of, including mission space. So some people kind of put us into the box of, yeah, these guys are just flying little tiny things, but that's not true. There is no mass limit here. It's just a question of scale. So here is a function of the array size. So there's bigger is better in our case, because you want the beam to stay on the longer to keep it propelled longer, so it's faster. So this is speed, and this top purple is 10% speed of light, 1%, 0.1, and 0.01%. Chemistry is down here, a little below here, well, around 0.01% approximately, a little below that. So this is 1 gram. This is a kilogram for something, a CubeSat class mission, and this is something comparable to Voyager, 100 kilogram class missions. And as you can see, we're capable of achieving relativistic flight. Just a question of the size of the array and the flux in the array. So the black line is 100 kilowatts per square meter, the red is 10 kilowatts per square meter, and the blue is 1 kilowatt per square meter, which is basically the flux light on the surface of the Earth. You're not talking about, you know, Death Star class power levels here. You're really talking about things which are large, but they're not outrageous large. Again, roadmap is the key operative word. This is a stepping stone along the way with lots of exit points. We're kind of down here at what we call phase 1. Things on the desktop, meter scale classrooms, you know, like a tactical system if you want to think of something currently realized. And we have stuff that works well in the laboratory here. We also have things that work well in the laboratory all the way beyond 10 kilometers in terms of phasing solutions. What we don't have in the laboratory is a full-blown packed phased array at the 10-kilometer level, which is bigger than our laboratory, by the way. But there's a direct path from here to here. Some of it is money. It's going to require a lot of development and a lot of funding to do it, but no fundamental reason. We've shown this. There's no fundamental reason. We've phase locked at an array size greater than 22 kilometers and shown we can achieve better than 100th of a wave over 22 kilometers. It's amazing. It's much better than I thought. So really a lot of it come down to economics as well as obviously technology to drive down economics costs. So there's kind of intermediate phase here where we talk about sort of 10 to 30 meter class array systems, which are great for preliminary missions, say you want to go rapidly for testing the moon or powering the moon, or rapidly in the solar system small missions. So these are not that gigantic. They're about the size of large optical telescopes. This is a chart I've shown before. I would really like to spend some time looking at this. And even if I don't give you all the nerdy stuff, which you're about to see, this is the one to really concentrate on. This is for the indirect drive. This is the ACTA paper that's published. And this is various missions, fly by Mars in 45 days, fly by Jupiter in a year, transfer to Mars orbit in 45 days, transfer to Mars orbit in 30 days, getting humans to Mars with the 5,000 ISPs, so not very exotic ISPs, and the 10,000 ISP ISN. This is wet mass 10 tons. This is wet mass of 100 tons, delivering 15 tons to Mars. So this would be a human class mission. How big is the array? That's of order a bit less than a kilometer with power levels, you know, hundreds of megawatts. The one to really concentrate is not these. These are aspirational, as is relativistic flight. It is this one, sending a CubeSat-like mission with a wet mass of 10 kilograms, flyby mass of 4 kilograms. How large is the array you need? It's not that large. It's about the size of the building that you're in right now, assuming that you're in a small size building, 10 meters, the size of the Keck telescope, with a power level of about a megawatt, gets you a speed faster than any chemical can achieve. That is not a high pole to think about over the next, say, decade or so to achieve. And it's this kind of mission that I would strongly urge people to understand that is one of the off-ramps in the roadmap that we're on. Okay, well, this is just a chart of, you know, getting places rapidly, 5 AU in a year, 40 a year in 5 years. These are things that NASA has to look at. Mars in 5 days. These are Mars and landing or going to orbit 45 days and Mars in 30 days. You have to drive down the alpha, you know, get the power up per unit kilogram, get the kilograms down per unit power. And because we don't take the power source with us, we can actually do that. In fact, we're already at about a kilogram per kilowatt with existing technologies today without the exotics. So we're already at an incredibly nice. If you want to, think of something kind of out there and not something we're advocating at the moment, the best you can do with humans and not liquefy them along the way is drive them at roughly 1 Earth G or a couple Earth G. And so you get to Mars and land in 2.5 days at 1 G and kind of never know you left Earth. This is not something you do today because the power levels are prohibitive, but it is the roadmap and in the long-term future, send humans rapidly back and forth, ping pong them to Mars, and just have a party for 2.5 days, you end up on Mars. That's direct drive rather than indirect drive. So we're here in April to June. We said we'd do all these things. We've done most of them actually. We're a little behind schedule, not too much behind. Next set of tests now, since we've gone indoors, is to go outdoors. And we're doing pretty well. I'm really at their team, even though it was a horrible year in terms of logistics, given the COVID situation. Okay, now I'm going to show you the really nice stuff. You can go to if you want, or turn off and do something else. This for us is the proof that things work, or the problem area. It doesn't work. Well, it's working really well. So we just demonstrated with a completely bidirectional phasing solution, which is exactly what we proposed back in 2009. And now we've shown in the laboratory with data that it works. So we have a sort of at scale optical amplifiers built and developed as a part of this program. We put together 3 of them just because of cost and schedule constraints. And we can phase lock to a beacon all the way down to 3 nanowatts per sub element, a very robust locking at a microwatt, weaker locking down to 3 nanowatts. And we even went down to 100 picowatts with our previous systems without the amplifiers. But this is a fully bidirectional optical amplification system, really quite interesting from a quantum mechanical point of view, because you're pumping power out one side at the same time you're receiving very few photons in the other side and amplifying them. It's amazing that it works, but we've shown that it does work. It's pretty messy on the benchtop. I wish it were not so messy, but currently it is messy. It does work. In the long run, you want to reduce a lot of this to photonic integrated circuits. It's another part of a long-term roadmap, but this part works, and it's really critical that it works. And we've shown now that it works at scale. We build our own photonics. Almost all of our work is done in our lab. We build our own amplifiers, and we've now achieved about 30-kilometer phase coherence lengths, which is great. It's a bit longer than we need, but it's really works well. And then we've shown we can take the beacon per sub-element down to the nanowatt level if necessary. So this is a technical area, but I'm happy to talk about it if you're interested. This is really where things work or don't work. And so far, we're really excited that it does work. This is a picture of phase locking. You'll see we turn on the beacon here. So this is a beam pattern of 3 elements phased together at full power, locks really robustly. And we have a paper out, the Optical Society paper and the SPIE papers that discuss atmospheric perturbations in the presence of beacon locking. So all I can say is so far, so good, works. This fact that you are simultaneously amplifying in both directions is really interesting, is that you can have very few photons coming back in from the beacon at the same time be blasting out, say 100 gigawatts of power in the total system and amplify this really weak signal coming back in. It's truly amazing that it works, but it does work. And there's very little additional noise. In fact, as far as we can tell, we're getting pretty close to a quantum mechanical limit. We're trying to understand exactly how far away we are from it, but it works better than I had hoped. So anyway, lots of components. It's messy right now. Apologize. That's the realm of photonics. Again, all this stuff is built, as you can kind of tell, in our laboratory because we have very specialized needs. Anyway, it's done by, in our case, we pump ytterbium doped fibers to achieve amplification. Efficiency is around, for the best we've done is around 43% efficiency, electrical to photonics. We blow up lots of things in the lab because the flux levels inside are in the 10 to 100 gigawatts per square meter inside the fibers. So you got to be very careful you don't have dirt in the fibers. We've blown up lots of fibers, but we fuse all our fibers together ourselves so we can make really nice connections. But you do have to be extremely careful. We also obviously take precautions with our eyes. Okay, yeah, phase extraction. So the basic idea is you use a coherent source as a beacon, you measure the phase at each sub-element, and that gives what's called a phasing solution, namely how you adjust things to get the beam on the target fully phased. Very analogous to adaptive optics in astronomy, except they're measuring curvature in the phase front. We measure the phase directly, so we have an advantage. Mechanical designs, whatever. There's lots of nuts and bolts literally in the system. The sub-elements are about the size of your arm and about the diameter of your fist. You don't want them too large because of if you want to use them inside the Earth's atmosphere, you have to keep the size small enough to be within the isoplanatic patch of the atmosphere, which means the size for a good site is about 10 centimeters, which is what we're using. So lots of stuff inside. I'm not going to bore you with it. It is a modular system. You build each sub-element and then you just multiply them. They're all the same, so you can go into mass production. So for our program for Limitless, we said we'd build 3. We've now built 3, but now we're about to kind of quote weaponize them by putting them into these tubular elements, and then we can array them. We'd love to build more. It's just a financial issue. So. Okay, this is what it looks like in CAD. There is lots of stuff running around. The red stuff is fibers, and then we build our own electronics to protect stuff, which is really important because if something goes wrong in the system, you start back propagating light through the system because it's bidirectional. You suddenly end up with a huge amount of power in a place you don't want it, and up goes the smoke. So we've built a high-speed monitoring system to protect it, and we've used that protection many times. It's a little bit rough at the moment, but it's getting better. We design, build all our own electronics in-house as well. Okay, this is a fiber tip actuator. This takes care of the tip tilt corrections for the first order atmospherics, and then the higher order corrections are all done in phasing through the phasing solution. And then we have a focusing mechanism so we can change the size of the beam depending on how far away the target is, because sometimes you want to hit targets that are close by. These are relatively small. This is about 2.5 inches or 64 millimeters. And again, what this does is move the fiber tip around so you can do the tip tilt corrections. This is what it'll look like for this program. It's conceivable, we might be able to get up to 7 elements. It's just a financial issue here. But this is if you have 7 elements, again, we promised we do 3 on a mount, and then we would array it in different ways depending on what the target is. In our case, the target will be a ground target to show that we can phase out to multi-kilometer distances. I haven't shown you the work which is published now on phase locking over large distances. We've gone out in the lab. You can do large distances by coiling fiber. We've gone out to 25 kilometers, which is the equivalent of a 50-kilometer diameter system, bigger than we need, and show we can phase lock. Our best data is at 11-kilometer radius or 22-kilometer diameter. We've shown basically about a nanometer or lambda over 1,000 is what we're capable of phase locking to. That's pretty incredible. You're getting down to atomic scales at that level. To some extent, we're kind of like LIGO, but we don't have the subnuclear requirements in terms of sizing of precision. Okay, so this is the NASA Luster program, which we consider to be kind of low-level, low-hanging fruit, which is, land a Nova C or something equivalent. So we've been working with Intuitive on this, which we're very excited to work with them as a possibility for the future. NASA's not funding us to land anything at the moment. They're funding us to develop the technology so that we could propose to land something and then beam to a rover in for example, a permanently shadowed region. This is the actual Shackleton crater. This is a bit bigger than we're looking at for the Luster program. Asked us to look at beaming 1 kilometer. We can beam well beyond that. So this is spot size as a function of target distance. Shackleton crater would be out here at say 22 kilometers roughly. NASA asked us to look at 1 kilometer. This is the spot size over here in the blue line, and this is the flux on the target in red over here. Don't worry about the flux on the target at the moment. We've been asked to beam 100 watts of electrical power, which means we beam about 200 watts of photons out to the target. And we do that routinely in our lab. So we can literally, we can beam many hundreds of watts in our lab for this power beaming type of experiment. So this is really neat. We love this kind of work. The one we really love to do, and we've been talking to Intuitive about this, is the following experiment. Land a system on the moon with a phasing beacon, have an infrared camera on board to take a picture of the moon, phase up, say 3 elements. This is a 3-element simulation on the moon, and you'll get spots. So we could write a children's book, how the moon got its spots. And what you'd see is a pattern on the moon of spots, which is an interference pattern of actually a 3-slit interference pattern, except have some circular symmetry. Get this beautiful set of spots on the moon, which you can picture. And you move the spots around. You could make a little movie on the moon. This would be an awesome experiment. It would also go a long way towards proving ultra long range power projection. So this is, as shown, we have a 100-meter circle on the Earth. We put 3 elements on that hole, and then we phase cohere to the moon using the phasing beacon on the moon, which is about the right distance for phasing to a relativistic spacecraft that you want to shoot out, say one of the wafer cell spacecraft for our Starlight program or our Breakthrough Starshot program. We'd like to be able to show you could do this. This would be a wonderful example of a midterm kind of solution to show that this works. Okay, I'll stop there, and happy to take any questions, Bernie. Hey, it's funny that the beeper didn't go off.
You beat it by 55 seconds.
Oh, darn! I'll have to try harder next time. All right.
I was going to say I'm going to be denied today. I'm not going to get a chance to have my little alarm go on. So, but that's all good, right? So, thank you, Phil, for a wonderful presentation. Maybe if you would go ahead and stop sharing your screen, and that way we can everybody can see the speakers. So thank you, Phil, for your talk. We'll switch into some Q&A mode here. I think we did have a question from one of the panelists. Adam, I think you had typed something in. If you want to just come off mute, you can ask it directly if you want.
Sure. Can you hear me?
I can.
Okay. 1 second. I really like this stuff a lot. It seems pretty clear that it's definitely the future. Random thought first before the question. Isn't this Tesla's original idea of beaming power, and then people thought he was insane?
That's I love your statement. And if I had much more time, I'd show you some slides on Tesla's New York and Colorado power beaming. So yes, actually, I talked recently where I took it even a bit further. Tesla was one of the time points I put it on, but I started a little bit earlier than Tesla. Namely, I went back to the Big Bang, and I showed that, if you think about it, we're alive today because of power beaming. We have a big power beaming system in the sky called our sun that works really well, keeps us alive. So we exist because directed energy works. In the case of the sun, we call it misdirected energy, but whatever. The universe kind of exists because light is beamed across vast distances that is also coupled with matter. Most of my work is in cosmology, so this connection between matter and photons is a very deep one in the universe itself. But if you ask, so what in our everyday life is power beaming? I happen to solar panels on my roof. When people ask, well, does it get tired and stop moving over vast distances? And I said, do you ever go outside and see the sun? Or do you look up at the stars? And it pretty clearly, people there's a misconception here that somehow, the light tyrant just can't go over vast distances. Clearly it does. Tesla, Tesla was absolutely brilliant. He was a little bit misguided in this one area where he looked at, could you power beam with a kind of what I would call near field technology. And now, of course, we use near field technology for, credit card transactions and other things at stores. So, yeah, I don't have any problem. We would love to get the Teslas of the world to say, hey, we'd like to, help you guys out here or take over, whatever. Yes. So I think the answer is a very affirmative yes, that power beaming is all around us, including all of you that have Wi-Fi on at the moment, which is probably virtually all of you, including myself. And it's a question of perspective here. What we're looking at is beaming, I would say, very macroscopic amounts of power over large distances, where large sort of solar system distances. And the emphasis is on macroscopic amounts of power. Clearly, the sun figured this out a long time ago, like billions of years ago. The sun figured out that it could send power to the earth. But what we're interested in is directing that source of power. Let's say we take a nuclear reactor from the work that we heard about this morning, and we use that to power a directed energy system. One of the concepts for the Luster program is use a kilopower class system, maybe have a 1 to 10 kilowatt reactor, electrical output reactor on the moon, and then use that as input to a system like ours, and then direct that power, in our case, near infrared photons, over just some photoconverter and then convert back to electricity. So it's a wireless technological solution. So some of the things we've been talking recently with Intuitive about, they asked us to look at this question. Hope I'm not saying anything shouldn't say here, Tim, but that's a great question you asked me one day when we talked. Is it okay to?
Yeah, go for it. Okay. Let's innovate.
Yeah, okay. So Tim asked me a great question, which I think was asked of him, which is, what's the trade space between the mass of wires that you'd have to lay out, say, a 10-kilometer link on the moon, or 100 kilometers, versus the mass and efficiency of a directed energy system? Very logical, very reasonable question. And then the way I look at all this, not just sort of blue sky, paper writing, which I do enough of, but how would you actually do that? So I'm a very nerdy person. Read my papers, you'll soon learn, how to go to sleep at night. Is that I ran a set of simulations of wire mass per unit length and, for a given mission space versus efficiency. There's some loss in the wire since you're not using superconductors for most applications, versus the mass efficiency of a directed energy system. It's a very logical question. If you want to get power from the sun to the earth, do you use an extension cord? No, use light. Okay. If you want to get power inside a computer, do you use light? No, use wires. So there's a trade space, where this makes sense, and a trade space where it doesn't make sense. A totally logical discussion. In the case of what Tim asked me, I think that the tipping point is around 1 to 10 kilometers for power levels of, order kilowatts or to hundreds of kilowatts or so. That's the power is not the issue. Where you would look hard, ignore the mobile situation part of this. For some applications, carrying an extension cord doesn't make sense, like my car. Okay, I don't want to carry around an extension cord for a car. But if you're just trying to ask the question, what is the minimum mass solution? Not even, other things, just what's the minimum mass solution? You come to the point where you say, if I want to send power, let's choose a number, 100 kilometers on the moon. Well, as I go to longer and longer distances with wires, I have to make them thicker and thicker to maintain this efficiency, i.e. deliver a fraction of the power I put in. Therefore, the wires get heavier. The mass increases for that length. And so there's a trade space where you'd say, well, that doesn't make sense. Instead of carrying all those wires to the moon, why don't we have a directed energy system and transmit the light via photons? And a perfect example of a very practical question. And I never really thought about that, Tim. So thank you for,
Yeah. Well, and I think that's still timely because, the big concern with the fission surface power call that NASA has out that'll be later this year that we talked about with X Energy. they want nuclear power for the habitats, but they don't want it close to the habitats. So it will be a distance power problem. And this is something that we need to look very seriously at.
Yeah, and I agree. I mean, in some applications where we want to beam power, say, a personnel carrier or a road excavator, or, in the Luster program, and, PSR, there's some applications where wires don't make any sense at all. But in the application that you asked me about, Tim, I think it's a fascinating question. I'd never really pondered that. So when I ran the numbers, the tipping for using conductors, copper, aluminum is actually a little more favorable because of the mass, is that around, I would say, 2 kilometer-ish, you should seriously think about not using wires, but using a directed energy system. And, people are scared when you use the word laser. And I have some hilarious about using laser pointers and not being allowed to use a laser pointer in a DoD facility where they're building tactical weapon systems to shoot things down with lasers. But you're not allowed to use a laser pointer system because you might point in somebody's eye. It's like, really? But yes, really. So people are afraid of that, but it's just, right? I mean, your body, okay, a little bit, the coherence makes a little bit, very little difference. It was really just how many photons, hit your eye per time. So, I like Dr. Strangelove kind of attitude. Just lose your fear of and embrace the light in this case. Anyway, I really wanted to work on this collaborative mode where we take the technology we're developing and have developed and apply it to application spaces that make absolute sense. And I know when you use the word interstellar, I apologize to all my colleagues, including the ones I work with, that when you use the word interstellar, people tend to close their eyes. But there are very logical reasons why you want to apply the same technology that allows interstellar to very niche, real world problems. And directed energy or paths of order tens of kilometers on the moon is one very nice sweet spot for applying this. And it's very practical. The laser efficiencies are a bit over 50% now. And the converter efficiencies are also around 50%. So currently the best sort of quote round trip, is efficiencies around 25%, electrical in to electrical out. Okay, that'll get better. We're getting better, all the time. We use 50%. There are some systems now that are close to 70%. Converters can be even higher. There's some photoconverters that are next to 60% efficient. So this is a really interesting space you're working in. You're not factors of 10 away from achieving, really high efficiency. You're within factors of 2 of unit efficiency. And the mass per unit power of the photoconverters is incredibly low. We're already below 1 kilogram per kilowatt on the photoconverter side. We're doing nothing special, not even going to thin film perovskite type converters. We're already at 1 kilogram per kilowatt with indium gallium arsenide. Also, we've used some very specialized silica band gap match converters. I don't know, it's a fascinating area. So we're really excited about the future.
Phil, I got a couple of questions that have been coming in the Q&A box. If I could bring a couple of them up for you. Got a question from Lance. Does the diffraction limit of the power beaming constrain the max distance at which momentum can be usefully transferred? And what would be the distance for a 1 kilometer aperture?
Yeah, okay, so great question. And actually you can do the math in your head. I grew up, I didn't have a calculator until after I got my PhD, so I learned to use my head and a slide rule. A 1 kilometer aperture at 1 micron, which is the wavelength we work at, which is 1.06 microns. Use a micron, divide by the distance, lambda over d. So it's micron 10 to the minus 6 divided by 10 to the 3 is 10 to the minus 9. It's a nanoradian. So a nanoradian is approximately your beam spread. Yeah, the factors of order unity. It's a nanoradian. You look at something like the Event Horizon Telescope, which is imaging the accretion down black hole. They're about 1/10 of a nanoradian, using the whole Earth as their baseline. So we achieve 1/10 of a nanoradian at 10 kilometers of baseline. So we're actually about the same, just to put it in perspective here. So a nanoradian at 1 AU, so let's say you're shooting at Mars, for example, a 1 kilometer array at 1 micron operation puts a spot at 1 AU, i.e. Mars, of about 300 meter diameter. A 10 kilometer array puts a spot at Mars at about 30 meter diameter, approximately order unity corrections. So yes, diffraction simply is the spreading of light with distance because you have a finite aperture size. The bigger the aperture, the smaller the spot you can put at a given distance. For the systems that we're looking at for relativistic flight, the early ones, if you want to think of it, the early ones, would be relatively small diameter reflectors of order, meter size. So there we would accelerate them out to, avoid lunar distances before we just say, look, it's not worth it to go much further. Yes, I think the word used was useful momentum transfer. So that's a great word to use because, there's no limit in distance. You just get weaker and weaker fractional momentum transfer. So at some point you just cut it off. I don't know if that helps or not.
Great, thank you, Phil. I appreciate that.
Sure.
Got just a couple more. Let me see here. Good question from Robert Kennedy. Any worry that the spillover from power beaming photons, permanently shadowed crater, might evaporate the water you're hoping to harvest before you can harvest it, right? Like you're beaming to that little rover, thinking like your NASA luster.
Sure. Okay, so that's a great question. So you could tip that one on its head and say maybe I could use the laser light in the PSR to perhaps look for water by vaporizing parts of the surface or warming it, maybe looking at the plume. We have another NASA program looking at molecular analysis using beamed energy. So in terms of spillover, yes, there is some spillover in the sense that the beam is not, collimated 100% within a certain size. There is some spillover that happens due to side lobes in the system. Typically for us in a well-designed system, we can keep the spillover, for example, in the Luster program, try to keep it to well under 10% of the power will spill over, not intending it to be, and we can make it less than that. It's really a flux question. How much power per unit area are you spilling over? Because that one will determine the evaporation rate or the ablation rate if you really crank up the power levels. We've looked at this. I wouldn't say we've done a proper mission study because it really depends on what level of evaporation are you willing to live with. If you're worried about evaporating all the water that you're going after, that's not an issue in general, because you would have to put in such a large amount of energy because it's pretty formidable. But you can use this to your advantage. So there's an issue there, but I think I consider it to be extremely small. You're not going to get rid of water, but I think the reverse problem is more interesting. Maybe we could use the same system to look for water subsurface wide, heating the surface and then looking at it with a kind of remote observation technology. Look at the molecular effluent that comes off.
Cool, cool. Thank you, Phil. You dropped out just a time or two. If it continues, we might have you just stop sharing your video, and that way the sound can come across. But I think we only have. Sorry, go ahead.
I'll turn off. But
okay. So I think we only have time for one more question, and then we're going to take a break. And this is just from my curiosity. What got you into thinking about space exploration in Interstellar? If you can do that in 2 minutes or less.
Yeah. Okay. I grew up in the 1950s and 1960s. Like many people in the United States, as a child, I was fascinated by the program. Actually applied to be an astronaut, and when a candidate got into the final selection, as I think I've talked with you about, and they found out that I had a little bit of spina bifida. It's not a problem for me, but in general, it could be a problem if you have to eject. That was a bummer. I've always been fascinated by space exploration, not so much for the full reasons of space exploration, but just because of it's almost an existential view of space. Is there something beautiful out there that is vastly beyond what we have on Earth? So I suppose it's more of a spiritual or it's kind of romantic view of life. In terms of technological work, I'm a very mathematical person. I started out as a theoretical physicist. I love thinking about things in very mathematical terms. I was doing some work on terrestrial threat mitigation systems, and just thought, what would happen if you just scaled it up? What would be the problem in scaling up? What could you do with it? And that then led to the idea of planetary defense using this technology. And that led literally within a couple of weeks to using it for propulsion. So for me, I love the idea that we can do something useful in life, to aid humanity. And one of the areas that I love is thinking about humanity going out and exploring not only our solar system, but going beyond that as a way of providing a bit of a stress relief from all the problems we have here on Earth, maybe by going outward. And I know people object to this. They said, solve your problems first before you go out. But I actually think by going outward, you actually help solve some of your problems by bringing people together and showing them that they can have a common purpose and not be hitting each other with clubs, but using your clubs to knock it out of the park and go explore somewhere. It's just who I am.
Thanks, Phil. It was a great answer to a question. Maybe it'd be even better to have that discussion over some beers or something in person at some point in time.
Totally agree. Yeah, I agree.
Right.
Yeah.
Right. So, I think with that, we've finished the morning session of today's briefing. We'll have a couple of talks after a short 20-minute break, where we'll get a talk from John Bush talking about some of his development of a hydrodynamic quantum field theory. And then Setthivoine You will talk to us about his work on another fusion propulsion concept. And so that should wrap up the day. So, but now we'll go ahead and take a 20-minute break. But before we go, I just want to do a hat tip to our partners on this Interstellar Initiative grants effort that we're doing. Texas A&M has been very instrumental in helping us with the implementation and execution of all the contractual side of things. So we're very appreciative of their efforts and help in that capacity. And we look forward to continue to grow that relationship. And then certainly our friends at Breakthrough Initiatives. We've got, I think Pete had to step off for a little bit, but perhaps he'll be back with us shortly. But we've got Dylan O'Reilly and James Shawick they're on the loop with us today. So big hat tip to Breakthrough. And in some discussions for the out outbriefing, which we'll probably be doing at some point in time in the October timeframe. I'm very hopeful that we can do that in person. Here in Houston, potentially we're looking at a couple of venues, but that'll give us an opportunity to be able to sit down and have some food together, break bread, and maybe share a beer and have some of these more philosophical discussions. And maybe we can have some other folks also join us in that venue. But with that, let's go ahead and take just a 15-20-minute break. We need to be back and at it by 10:30. So it is currently 10:12. Be back at 10:30. I'm going to go ahead and put my share screen up to have the schedule as our splash screen while we are taking our break. So make sure you mute all the panelists. Make sure you mute your computers. So be back in a bit. Thanks, guys.
Hey, Sonny, how you doing?
Hey, John.
I'm fine. Thanks.
Oh, that was Siri. That reminds me. You gotta turn Siri and Alexa off when you're lecturing these days, or they'll both pipe up, start talking to each other.
That's funny. Oh my goodness, John. That was absolutely funny. That goes really well with the comment during Phil Lubin's talk where he talked about autonomous driving on Earth is nice, but eventually we will want autonomous spaceships, right? So
You have to change your. You have to change your name during the pandemic.
right. That's funny.
Sonny's too close to Siri. Uh-oh, here she comes again.
Right, absolutely. So, yeah, I'm really looking forward to your talk today, man. Glad you got a chance to.
I'm happy to join. I got distracted. I did a little bit of COVID work, which was all over the press recently.
Oh yeah, yeah.
Owing to an imprudent interview given by my co-author, but.
Okay, I gotcha.
But, then some good press followed, but it's kind of nice. We derived basically a time limit for an indoor space, right? Because the scientists have long known that it's airborne, but they didn't have a sort of guideline. So we have one nice equation, and it tells you how long you can stay in a space as a function of all the relevant parameters.
Oh, interesting. That sounds like some very interesting work. Yeah.
As a fluid mechanician, one has to pitch in during a pandemic, right?
Right. We contribute in whichever way we can, right? So
I was amused by Phil's thing about the laser pointer, and
hey, you can't have that on in here.
Because it's like people have COVID-related social distancing guidelines being foisted on them when they're working in Ebola labs, right?
Right.
It's just totally ridiculous.
Right. That they have bigger concerns, right?
Yeah. They know how to handle things.
All right, so it's 10:29. I'll just go ahead and do the wind up here with an introduction to John Bush, who will be our next speaker. And so John will be talking to us about his work with his hydrodynamic quantum field theory. The title of his talk is Assessing the Viability of Quantum-Based Propulsion with Hydrodynamic Quantum Field Theory. John Bush is a professor at mathematics at the Massachusetts Institute of Technology. So with that, John, I will hand the microphone over to you, and you have control, and I will set the timer, and we'll see if you win the timer award today. So far, nobody has won today. So.
I fear the red alert, as I feared the green frog last time. Okay.
Right.
Very good. Well, thank you, Sonny, and thank you all for attending. It's a pleasure to join this midterm meeting. I'll be talking about work which has been done primarily by my postdoc on the project, Adam Kay. So you'll see a discontinuity in fonts throughout this talk, which will account for the fact that I've created some slides and him the others. Okay, so again, this is all about trying to see what we can learn about microscopic physics from this hydrodynamic system, which has recently been discovered, in 2005, and has been the focus of my research for the last 10 plus years. So in terms of hidden variable theories, these are basically theories which try to have a theoretical description of particle trajectories on the quantum scale. And it turns out that all I wouldn't say all, but many of the most successful hidden variable theories have involved microscopic particles interacting with background waves of some sort. So before the notion of hidden variable theory was even out there, de Broglie proposed a double wave pilot wave theory of quantum dynamics. He imagined a particle as having an internal oscillation, interacting with the background field, creating a pilot wave, and then being guided by that wave, and then giving rise to statistical behavior, which is described by the standard quantum theory. Bohm also, he presented a slightly simpler version, which was not rooted in relativity. It involved a particle moving in response to a pilot wave, and it's basically deduced by a sort of mathematical reformulation of the Schrodinger equation. And it also has had some success. Nelson proposes stochastic dynamics, which involves particles interacting with a background field, and basically, as a result, moving through a sort of diffusive process where the diffusivity is prescribed by h bar over m, which, so this is sort of a structured random walk, and we'll see that this hydrodynamic system, which I'm describing, and the theoretical abstractions thereof actually touch on all of these have common features to all of these previous pilot wave theories. Okay, and the last one I'll mention is De La Peña and Cheto. So they've developed stochastic electrodynamics, in which they see any charge particles interacting with the electromagnetic quantum vacuum. Okay, and so what set me on this path was this discovery of the hydrodynamic system by Yves Couder and Emmanuel Faure in 2005. So they basically found basically a macroscopic realization of the sorts of dynamics that Louis de Broglie proposed in the 1920s. And lo and behold, it exhibits several features of quantum systems. So this whole research program has been aimed at first identifying the key dynamical features responsible for the quantum-like behavior in this macroscopic system, and those we now understand well. And we're currently still exploring the potential and limitations of this hydrodynamic system as a quantum analog. And the work which LSI has been funding has been largely towards developing this, so projecting from the hydrodynamic system and trying to develop a rational theory for quantum particles on the microscopic scale. So can we come up with a rational theory for quantum dynamics? And so just briefly, the hydrodynamic system involves a drop walking on a vibrating bath. So the bath is vibrating at a close to the Faraday threshold. The Faraday threshold, you would generate waves even in the absence of the drop, but because we're below that, the interface would be flat were it not for the drop. So each time the drop lands, it basically generates this basically a Bessel function form. So you have a monochromatic wave field, and at a critical vibrational forcing, the bouncing state becomes unstable to a walking state. And again, these things don't coalesce because the contact is short relative to the time needed for the air layer between them to drain. And so the interface basically behaves like a linear spring, and the drop then self-propels, as you can see here, slowly from left to right. This is, they're basically moving at about 1 centimeter per second. In the scale, the drop is about 1 millimeter. Okay, and so the key features responsible for the quantum-like behavior are the resonance. So basically the drop bounces at the most unstable wave mode of the vibrating bath. So you have a resonance between the bouncing drop and its underlying wave field. Secondly, and it's by virtue of this resonance that the wave field accompanying the drop is monochromatic. If it was bouncing around randomly, you would get the accompanying wave field would not be so structured, and it's this structure which gives rise to quantized states. And the real key feature, which is ultimately responsible for features akin to quantum non-locality, spatial non-locality, is the temporal non-locality of the system. So basically, the system has memory. So the instantaneous force acting on the drop depends on its pass through the wave field, because in order to, of course, it's local. The system is entirely local. The instantaneous drop force on the drop just depends on the local slope of the interface beneath it at the point of impact, but that slope is determined by its history. So you have to integrate back in time to calculate the wave force on the particle. And so this is what renders it non-Markovian hereditary. We say that system has memory, and we take memory as a proxy for how hard we're driving the bath. So as you drive it harder and get closer to this Faraday threshold, the waves are more persistent, the memory is longer, and you have to integrate backwards in time to describe its dynamics. Okay, and as we'll see, and well, let me just say that in the hydrodynamic system, again, it's this memory which is responsible for the apparently spatially non-local effects. So it gives rise to many situations where if you didn't acknowledge that the forces were wave mediated, you would infer the system was non-local. Okay, and it's because basically the drop is carving out this topography as it moves along the surface, and then it's navigating that same topography. And so the topography then effectively plays a role of basically the quantum potential in Bohmian mechanics. Okay, and so this has been the source of all sorts of hydrodynamic quantum analogs, so that we now have a growing grocery list. So we have orbital quantization and spin states in the system, and again, its theoretical abstractions, tunneling, Friedel oscillations, single particle diffraction, and also optical effects. And I just want to highlight spin lattices because we have something new coming out. It's in Precedent Nature at the moment. So we basically have a spin lattice achieved with these walking droplets. Okay, and so again, this is a hydrodynamic system. It has limitations which preclude its capturing certain features of quantum mechanics. In particular, viscous damping of the pilot wave is our enemy. All the quantum-like features emerge as you approach the Faraday threshold, that is to say in the long memory or the high memory limit. And also there are situations where the drop inertia will preclude quantum-like behavior. For example, spin states are just slightly unstable in the lab, but in a more generalized theoretical framework, one can capture them. And there, it's basically a drop confined by its own wave field. Okay, so we've seen through this list of hydrodynamic quantum analogs what the key features are for the macroscopic quantum behavior. So what are the mechanisms by which these quantum-like features emerge? And again, it relies on the resonance between the drop and the wave, which gives rise to a monochromatic wave field. And the memory ensures that there's a trace of that wave field in the form of topography on the surface. So this drop is then navigating this non-local potential, that is its pilot wave. And so there are, again, three paradigms for this macroscopic quantum behavior. The first is orbital pilot wave dynamics. Basically, by virtue of the interaction of the particle with its wave field, so the dynamic constraint imposed on the droplet by its wave field is such that it ensures that there be a finite number of accessible dynamical states. So these are basically quantized orbits. And then when these orbits could become unstable, so as you increase the memory, they typically become unstable, and basically through some period doubling cascade or other transition to chaos, and then you get chaotic switching between the accessible quantized states. Okay, another mechanism for quantum-like behavior is in the form of inline oscillation. So if perturbed, a walking droplet will oscillate along its direction of motion with the wavelength of the guiding wave, and so that then gives rise to a statistical signature with that same wavelength, and so we'll see. So basically, the pilot wave in this system, the Faraday wavelength, plays the role of the de Broglie wavelength in quantum mechanics. Okay, and there's also situations where you get a sort of chaotic, quantized random walk, and so you get a diffusivity, which again looks like that arising in Nelson stochastic dynamics, with the Faraday wavelength here playing the role of the de Broglie wavelength in his model. Okay, so just big picture, prior to this this system, as far as I was concerned anyways, I was sort of strayed from modern physics into fluid mechanics for several decades. But there were certainly the picture when I was an undergraduate was that classical physics and quantum mechanics never shall meet. And then now we have this hydrodynamic system, this pilot wave hydrodynamics, and we see that it's sort of making intrusion onto the quantum territory through these hydrodynamic quantum analogs. And this has inspired the development of a theoretical generalization of our model for the walking droplets, which we call the generalized pilot wave framework. And this allows us to capture new features which are not accessible to the hydrodynamic system, but are features of quantum systems. And this, in turn, has guided us in developing. So now this hydrodynamic quantum field theory is the last step. And this is basically an attempt to complete de Broglie's mechanics informed by the hydrodynamic system. And this has also yielded some very interesting things, including, I now feel I understand from a purely classical perspective why P equals H bar K in quantum mechanics. Okay, so that's the sort of big picture. So we're just trying to tile the plane and stamp out that gold color entirely. So in terms of the LSI project, we're basically developing theoretical models of vacuum-based propulsion of particles. So our bouncing drop, the vibrating bath, is basically playing the role of the vacuum in these various quantum theories. And so to assess the viability of these vacuum-based dynamical models as a rational quantum dynamic. So in so doing, we hope to increase the fundamental understanding of the vacuum and inform the possibility of vacuum engineering. So extracting energy from interstellar propulsion. Of course, we have a vibrating bath. That vibrating bath ultimately propels the particle. So one can hope that can be used to propel larger things. Okay, so in terms of the approach, it's basically theoretical numerical modeling of these pilot wave theories. So both the generalized pilot wave framework and this hydrodynamic quantum field theory, which was originally developed with Yuval Dagan, who I know is on the call. And so basically we want to assess their viability in terms of quantum dynamics. So, and we'll talk a little today about modeling with both the generalized framework and this hydrodynamic quantum field theory. We basically want to go to 3D, and so look at motion in a simple harmonic potential and a Coulomb potential. Okay, so again, this is Adam Kay has been the driving force on this work. He's been more than ably assisted by Matt Dury, who's an instructor in our department and did much of the work on much of the theoretical modeling on the generalized framework in 2D. And Yuval Dagan will be called upon as soon as we get to the HQFT, which will happen in the second half of our program. Okay, so this was our proposed research timeline, and remarkably, we seem to be more or less on time. So we'll see what's left at the end of the talk, but we have made some headway, and again, we're pretty much on schedule. So this the hydrodynamic system, very complicated. We don't need to go into it, but suffice it to say that there are many dimensional and dimensionless groups involved, and we basically derived a trajectory equation. Again, it's a bit of a mess, but we can simplify it by saying, okay, this is worth noting. So the key feature here is you have this wave force, which depends on the wave field, which requires that you sum up all of the previous impacts of the walking droplet, right? So you have this differential equation that the memory enters through the wave force because the local wave field depends on the history of the particle. And you can see the appearance of memory here, which says basically how long it takes, how persistent the wave field is, and that depends on your proximity to the Faraday threshold. Okay, so you can actually strobe this, so you can describe the dynamics, which doesn't involve a walking drop, but a drop gliding. And so this is the so-called stroboscopic model. And then you can turn that infinite sum into an integral and imagine that the particle is continuously generating waves. And then you get this integral differential equation, which is amenable to analysis. In particular, we can look at the stability of the bouncing state, the walking state, and various orbital states. And this is sort of extended to the generalized framework and ultimately to 3D in what follows. Okay, so the idea is to take the key features of the Walker system, in particular memory, resonance, and this quasi-monochromatic wave field, which are responsible for all the quantum-like features, and then abstract that to a broader theory where one can hope to capture more quantum-like features. And this also provides a bridge, really, between the macroscopic systems for the bouncing drops and these previously mentioned quantum pilot wave theories. So it's really providing a bridge between, so this generalized framework provides, again, a bridge between the macroscopic and the microscopic, and will guide us as we develop the hydrodynamic quantum field theory in 3D. Okay, so first we did a sort of parametric generalization. So this is, if you just non-dimensionalize the governing equation of the stroboscopic model, and we keep a Bessel function form for the wave kernel, then there are two dimensionless groups. One prescribes the proximity to threshold, so basically how long the waves last, and the other prescribes the inertia of the system, this kappa naught. Okay, and what we'll do in what follows is we're going to relax this. We're going to say, okay, we don't have to have a Bessel function, we can have something else, and we'll see how sensitive it is to that. And again, so this has been very useful in informing our attempts to develop dynamics on the quantum scale in a manner originally suggested by De Broglie. Okay, so what happens in 2D? You can see, so with this generalization, you see that there are all sorts of possibilities so this is when we're above the walking threshold, but as we change the damping, we can, if we perturb the self-propelling particle, then you'll get overdamped oscillations here. So it'll simply relax back to its free walking speed. You can get these inline oscillations in this region here, and then you get this sort of erratic random walk, a structured random walk, which is again sort of reminiscent of what Nelson considered. And in this one parameter regime here, so in the high memory, low inertia limit, you can get these spin states where a particle basically zips around in its own wave field, confined by its wave, and you get these little slivers of parameter space where you get wobbling and sort of processing motions, okay? And so that's what you get in 2D. And of course, there are more possibilities when you go to 3D. But so if we look at this generalized framework now, we can relax the Bessel function, saying, okay, well, what happens if we look at an arbitrary pilot waveform? So again, when we non-dimensionalize, there's basically a term here, which is basically the magnitude, prescribes the magnitude of the importance of inertia in the problem. And then you have this the memory is characterized by this mu parameter, which is 1 minus gamma. So mu is 1 at the walking threshold, and in the high memory limit, it goes to 0, while gamma goes to 1. Okay, so the onset of motion, you basically take the walking state and you perturb it, and it turns out that the threshold for where the onset of motion is basically bouncing in place, and then we perturb it, and the critical memory at which motion sets in depends only on the local form of the wave function, in particular of the waveform, in particular the second derivative at the point of the origin. So it's kind of a nice result, and this is in 2D. This is consistent with the results of Villani and co-workers who looked at the various different wave kernels and how that influenced the onset of motion. Okay, so now what we want to do is go to 3D. So the physical picture. So again, some people have trouble abstracting this, saying, okay, because in 2D we have the drop actually literally detaching from its wave and then impacting. And so, of course, in 3D you can't do that. You're embedded within the field in some sense. But you notice that you can actually get floating objects to self-propel as well. If they're asymmetric, they can remain attached to the field and also self-propel. So this has been shown by Dan Harris Brown recently. And so the physical picture here is you have a drop pulsing axially symmetric spherically symmetric waves, and it's of course stable. It's everything symmetric, so you'd think it'd be stable on the origin, but if you perturb it slightly, it can destabilize into a dynamic state, precisely as the bouncing drop is sitting on a symmetric waveform, but if perturbed, it can self-propel, and it does so above a critical threshold, and we'll see what that is in 3D. So it's basically creating this spherically symmetric wave, which is radial and changing sign with time. Okay, so the critical threshold for self-propulsion, it turns out it depends, because it depends only on this, the local second derivative of the waveform at the origin. You basically have this result, a nice result, which scales with dimensionality. So if we choose in a 1D pilot wave system a kernel which is a cosine, in 2D we have a Bessel function that should be R there, and here's a 3D Bessel function. We just see that how this changes with dimensionality, and it's actually very nice. In particular, in the high memory limit, the relative magnitudes of the free walking droplet scales as the square root of the dimensionality. So it's square root of 3 in 3D, square root of 2 in 2D, and 1 in 1 dimension. So here's how the velocity changes with this memory parameter. And so as we cross the walking threshold, the drop will increase progressively in speed until asymptoting up at this high memory limit. Okay, and we can look at the stability of these walking states by, again, perturbing the free walking state, and this follows as really as it did in 2D. And so, and this is the map in 2D, and we're trying to complete this map now in 3D. So again, the analysis is very similar, and so we have, again, overdamped and underdamped regions. We do have this region characterized by a random walk. It's relatively small compared to 2D, but there again, the part you get the structured random walk, and here's where we expect to find the spin states again. So because it's in 3D, there there's a rich number of possibilities in terms of spin states. So you could have a spin state confined to a plane. It could be confined to a sphere, so sort of processing around with its spin vector changing as a function of time. And so if we look, so we do have these various states. We have basically a part, if we're below a critical memory, then the pulsing particle will just sit at rest. Above a critical memory, it will destabilize in its own wave field and start moving. And then it can be subjected, so its stability depends on, again, the memory. You can have overdamped perturbations, underdamped perturbations. You can get the structured random walk, and we'll see here that you can also get these spin states. So you can actually look for solutions in which the particle is moving at a uniform frequency, uniform radius, and there are solutions to this. So you get this coupled set of equations, and there are solutions, but the jury's still out as to whether they're stable. So we've been exploring numerically and not found any stable solutions yet. So here you can see something initialized on a circular orbit with half the radius corresponding to half the wavelength of the pilot wave, and it alas flies off into a free walking state. But we know how to do the stability analysis because we've done it in 2D, and so we're hoping to find stable spin states. Interestingly, in 2D, there were the smallest spin state was stable, but no other spin states were stable. So it may be, worst case scenario is there are no spin states in the generalized pilot wave framework. But again, I see this as a stepping stone to the hydrodynamic quantum field theory. And what's of course interesting is whether we're going to get spin states there. So even if we don't find them in this generalized framework, there's hope that we find them in the hydrodynamic quantum field theory, and the theoretical developments here can be directly applied there. Okay, and so again, we're going to see if we can get stable spin states. This is, I think, best done analytically by extending our work in 2D. And we'll also sort of sniff around if we do find stable spin states and see if we can find some of these interesting wobbling or precessing states, or whether we can, whether we can have a spin state characterized by, again, the spin vector precessing around in a random direction, which is kind of a nice physical picture. Okay, and so we've also started looking at the motion of a walker in a central spring force. And so this was sort of inspired by the hydrodynamic system, where one sees the emergence of a double quantization in energy and angular momentum. So these are trajectories from one of Couder's early papers, and you can see the path of the walking droplet here. So it's basically confined by central force. Of course, these walkers want to walk in a straight line at constant speed, but they're confined by the spring force. So they come back, and they do so. As they do so, they track out a series of, they have a preference for a series of periodic orbits. And when the system becomes stable, they will switch, becomes unstable, that is to say chaotic, they will switch between a finite number of accessible periodic states. Okay, and so this is what you get in 2D. So you get quantization in radius of the mean radius of the orbit, which is a proxy for energy. And then you have a quantization in mean angular momentum. So that is 0 for these lemniscates. So as you move along, so the red points here, and here you have the circular orbits of increasing radius. So you have a number of circular orbits accessible. And then as you go, as you weaken the spring force, you get these more complex orbital forms like these trefoils. And again, when the system, and this is sort of classic in terms of a paradigm for orbital pilot wave dynamics, you have a number of accessible periodic states. And when the system becomes chaotic, which is what happens in the high memory limit, the droplet will then switch between these unstable periodic orbits the result being sort of multimodal statistics, which are peaked on these, which have peaks corresponding to these different periodic states. Okay, so we go to 3D. So now we have a drop, our spherically pulsating drop, self-propelling in the presence of a radial spring force. So it basically sets off here, and it then loops back, completes this trajectory, and then locks onto a circular orbit. Okay, so these are hot off the press. And here we have, so here we can see the wave field generated by this droplet moving along a circle in this spring force. And so this motion is here confined to a plane. And what's interesting is to look at the evolution of the mean wave field for a circular orbit. So this is if we take that same simulation, we say, okay, what's the mean wave field? After 5,000 time steps, it looks like that. After 10,000 looks like this. After 15,000, so it sort of completed a loop there. And you can see it's actually carving out its own topography. So this mean pilot wave field is in some sense what the drop is seeing as it propels around. And so the emergent waveform is centered not that, so the mean wave field is centered not on the particle, now it's centered on the center of its orbit, okay? And so you can then, you can actually relate this mean wave field to the probability distribution of the particle through a convolution result. So basically, if you convolve the distribution of the particle, which is here just a delta function on this corresponding to this radial orbit, if you convolve that with the wave field of the pulsing object, then you can compute the mean wave field. And again, this mean wave field is an interesting object because it's basically what the particle is navigating in some mean sense. So really it kind of plays the role of the non-local potential in Bohmian mechanics, although of course it is local. It is being generated. We're just taking the average of a local field generated by the moving particle. Okay, so other things we see in with this 3D model. So we see lemniscate trajectories. Everything so far has been confined to a plane. So here we start off again with some arbitrary initialization, and it then relaxes to this lemniscate form, and the trajectory is here color coded according to speed. And so here we can see the wave field as the particle tracks out the meniscus. And again, you have basically it's a quasi-monochromatic wave field. These magnitudes prescribed by the frequency of oscillation of the particle. And so we get more elaborate orbits. So this is something we found in 3D that we didn't find in 2D, which is a 5-lobed or quintifoil orbit. And things here are basically, this is quasi-periodic, so it's not exactly periodic, it's slightly drifting. That was the case also in 2D, but it seems to be drifting within on a 2D, so hypersurface. Okay, and so then we can perturb. So what happens if we perturb one of these periodic orbits? So we start here with this object, which is again basically confined to a plane. If we perturb it, it will basically it just flips to another plane. You can see that from the side view. So this quintifoil will basically, in response to perturbation, out of plane, it will simply adjust the plane that it's in. So nothing too surprising there. And then we get, so when you get a very high memory, all of these orbits destabilize. So again, we haven't done a comprehensive sweep through parameter space, but we have found this region in the high memory limit where the thing is basically confined in some global sense by the spring force, but it's really executing a random walk, and it's a sort of structured random walk, we believe, where there's basically a change of direction. It changes direction on a length scale comparable to the pilot wave wavelength. And so then again, it's evocative of Nelson's stochastic dynamics. But I personally, in terms of trying to understand the emergence of quantum-like statistics, I don't like having to resort to chaotic dynamics and diffusive processes. I'd be much happier if we can have quantized periodic states and chaos giving rise to switching between those, but we shall see what happens. Okay, and so again, you have, there is this regime where things are no longer confined to a 2D hypersurface, but basically are exploring 3D space through this sort of structured random walk. Okay, so again, we want to see how the quantization, this is again the picture in 2D, so how the quantization changes in 3D. And so we will, in particular, is there going to be a triple quantization in 3D? So this we'll hope to find as we move forward. Okay, and so the last section that I want to mention is, so this is basically where we're going with this generalized pi wave framework, is we want to use it to bridge the hydrodynamic system to this hydrodynamic quantum field theory, which was developed with Yuval Dagan. And so the idea here was to extend de Broglie's mechanics informed by the pilot wave hydrodynamic system. So again, when he proposed his pilot wave theory, he didn't have a classical analog to draw from, so he didn't have the sort of intuition we have. In particular, how does the particle locally interact with its own field in such a way as to self-propel? That's a sort of pervasive problem in modern physics, even for the Lorentz-Dirac equation, looking at a charge moving in its own wave field. And so we basically did what de Broglie would have done had he had MATLAB, which is code up what he proposed, which he said basically consider a particle as a localized excitation in this in the Klein-Gordon field. So, and you imagine the particle is an oscillator at the Compton frequency, and you get that by saying equals h bar omega equals mc squared. That defines the particle of mass m as mc squared over h bar. So we view this particle as a local excitation in this field. And we also consider for the sake of simplicity, we consider the zero particle inertia, no wave damping limit. And so we basically have a relativistic guidance equation, which is prescribed by this coupling constant. So between the particle motion and the slope of the wave field. Okay, and so we found that again, above a critical threshold, this thing will start moving, and it will do so. There's a sort of internal inline oscillations at the Compton frequency. And we did some analysis where we actually calculated the critical threshold in terms of the wave amplitude at which the particle will self-propel. And then we found, so when we went from, this is 1D analysis here. So I should mention in the work with Yuval, that, I mean, it's sort of a nice feature is you see how P equals h bar k evolves, and you can think of it as follows. So if a particle is moving and dressed by a monochromatic wave field, then that wave field, its group velocity must match the velocity of the particle, and from that you get P equals h bar k. Okay, so it's kind of a nice physical picture. And if a particle is dressed by a wave field, if it's monochromatic, if the two are moving at the same speed, P equals h bar k has to follow. Okay, and so then we also see that we can actually see the form of the pilot wave when we go to 2D, and you see here as the particle propels, oscillating at, so self-propels and oscillates at its Compton frequency, you get this basically this planar waveform, and the planar waveform has the de Broglie wavelength. So it's very hopeful in terms of what might happen when we send these particles, for example, through slits. Okay, and so the idea is that as we extend this hydrodynamic quantum field theory, which is our ultimate goal, to 3D, is that this work will be informed by what we're doing with the generalized pi wave framework, because the mathematics of the two systems is so similar. Okay, so in terms of what's left, so we're going to basically take what we've done, we're going to complete what we've been doing with the generalized framework in 3D. So looking at the motion of a particle in the simple harmonic oscillator, so looking to see how the multiple quantizations emerge, and then use that in as we develop the hydrodynamic quantum field theory in the same direction. So we'll look at simple harmonic oscillators later, also the hydrogen atom, and then we'll continue, then we'll again develop this hydrodynamic quantum field theory to 3D and start looking at some canonical problems in quantum mechanics that we can sort of anchor onto and that we have looked at with the generalized framework. And so that's basically what we'll be doing this summer, is taking it from the generalized pilot wave framework to the hydrodynamic quantum field theory. So Yuval will be hearing from us shortly, and hopefully we'll have things to write up in the fall. So I also have avoided the red alert and the green frog, so I'm happy to take any questions.
Oh, dang, man. You were 7 seconds from it, right? Oh,
yes.
Oh, my gosh. I had the phone. I was holding the phone up. I was waiting to get my moment, man. Fantastic job. Fantastic job. Yeah, could you stop sharing your screen now, and then we'll
Sure, yeah, that's right.
Go to the presentation. Thank you. Thank you, John. Fantastic talk. Very interesting progress. Interesting thoughts and great progress. So thank you for giving us such a very thorough presentation today. And I think Phil had clipped a couple times in his talk about these talks being very nerdy and helping people go to sleep. But I think everybody that's here today in the panel and online, this is right up their alley. This is not putting anybody to sleep. We're all very fascinated by this stuff. So thank you, John. So we got some time here for some questions. Let me go ahead and open it up to the panel real quick. I think we've got a couple questions in the Q&A, and then I've got a couple on YouTube that I'll bring up. But let me open up the panelists first.
John, this is Philip Lubin. Those are a great summary. I really appreciate that from a fundamental physics point of view. If you look at this, not from a conservation of energy point of view, because that's not necessary in the general relativistic sense, but what happens to the local field as you extract energy from the field, as you transfer it from one part to another part? And are those effects observable in some way?
So in the context of the hydrodynamic system, or generally in the pilot wave?
It's kind of a more generalized question, and just theoretically, as you look at this from a fundamental point of view.
Yeah, so you see the background field. It has to couple to the, I mean, you can see, so there is a sort of issue as to whether the internal vibration itself, and this is a debate they have in stochastic electrodynamics, is the particle vibration itself intrinsic, or is it driven by the background field? And I think the verdict is that it is this internal oscillation at the Compton frequency is actually driven by the field. So it is basically extracting energy from the field. And then it is then coupling to that field in such a way as to self-propel. So the ultimate energy is coming from the background field. And that's true also in the walking droplet system. And as it propels along, it's sort of dumping energy back into the field with each impact, right? So it's transferring momentum and getting a little nudge forward. But ultimately, the energy is coming from the background field.
Thank you, John.
Does the temperature drop in the system if you look at it from a thermodynamic point of view, in not of the whole system, but of the local system of the field, transferring energy into, say, a particle or something macroscopic?
Yeah, so I have good intuition about this on the hydrodynamic system, less so on the quantum scale. But yeah, so I'm not entirely, I'd have to think a little bit about that. Certainly in the hydrodynamic system, you have these, you sort of have a separation of timescales, because you can have these steady states, for example, an orbital state, and the thing will orbit in a circle forever, and you know that energy is being pumped in, there's dissipation. So ultimately there's a time scale over which the bath will warm up, right? And so then the viscosity will change, the surface tension will change. So you get this very slow drift of energy being dissipated into the bath. But these experiments are done on a time scale. You can do temperature control in the hydrodynamic system and so eliminate that and really get a true equilibrium. But fortunately, the experiments are done on a time scale where you don't have to worry about that. But I do presume that something similar is happening on the quantum scale energetically. So I mean, the way I kind of view it, I mean, this is sort of slightly, yes, not at all well-founded or rigorous, but you can sort of view the quantum vacuum as there being sort of weather, like locally there are fluctuations, right? There will be a storm over here, and the field will break, give rise to particle creation and so forth. And just like if you had this bath and it was sort of, if you imagine the Faraday threshold was different in different places, right? So you'd have a region where you shake, the bath is shaking so hard, you're actually creating particles. In other regions, it's not shaking hard enough, the particles disappear. So you can sort of view that as weather, and I kind of have that physical picture in when I think of the quantum vacuum as well. It's the Dirac, yeah, it's my notion of the Dirac sea, which was, of course, so it's like a hydrodynamic analog of a hydrodynamic analog. Quantum vacuum as a sea. Yeah.
Got a question from YouTube from Eric Davis. His question is, does the hydrodynamic quantum field theory take into account the Lorentz invariance property of the quantum vacuum? He has a second related question, and can the model embrace the other vacuous structures? And he's speaking to quantum chromodynamics, Higgs, etc.
I'm very happy to have Yuval Dagan here. I believe the answer is yes for the first question. What was the second question?
The second question is, can the model embrace the other vacuous structure? So he's speaking to quantum chromodynamics, the Higgs field, electroweak.
Yuval, do you want to take a crack at that?
Yeah, sure. Hi. So as for the Lorentz invariant, yes, we are using the Klein-Gordon equation for the wave field, which is Lorentz invariant. And then the dynamic equation that we coupled it to is also written in a relativistic manner. So we believe that the coupled equation is relativistic.
Thank you, Yuval. Glad to have you on board.
Wow.
Maybe I could lean forward a little bit on QCD and Higgs. Maybe that's like a further iteration of things from where you are right now.
Yeah, so I mean, I like the, there are many notions, and I've been receiving an awful lot of emails about looking at gravity waves. I mean, as far as we're concerned, we're not wed to one field or another. Again, I think the most complete pilot wave theory is probably that of De La Peña and Cheto, and they look at this, the electromagnetic quantum vacuum field. But the Higgs field that's basically satisfies Klein-Gordon. So effectively, that's what we are looking at with HQFT. It's the Higgs field. And then there's the possibility of gravity waves. And my problem is with gravity waves is the formalism, but I've been finding formalisms which look less daunting. But I like that picture. If in terms of the physical picture that Dubois said, he said, okay, imagine a particle exchanging rest mass energy with field energy. Why not gravity waves? I mean, I would love this. So again, if anyone can help on that front, I'd love to see it. But right now, I mean, the nice thing about Klein-Gordon, A, it's describes the Higgs field, but B, it looks very much like the water wave equation. So I'm very comfortable with it. I don't have to worry about metrics or anything. So that's why we're starting there. But we'll see where we go, where this leads us.
Yeah, thank you for that's a great answer to that question, specifically kind of tying in the Klein-Gordon equation. I see that Remo has his hand raised here. So Remo Garantini, don't forget to unmute yourself when you ask a question.
Okay. Hi, John, I'm Remo. And your Klein-Gordon equation is relativistic in the sense of special Minkowski and so on, but I presume that it could be more interesting to see what happens when you put the curved field. So I presume that this is very complicated, but this is the goal. I mean, if you are going to think to something that this is going to interstellar and so on, you need something that goes into the curved space-time, not in the flat space-time, like the usual Klein-Gordon that you are using. Do you think that you can translate this in a different language with coupling with the gravitational field and the Klein-Gordon itself?
It's a very good question. I mean, this is exactly what I was touching upon. I've been getting this suggestion from many people, and I think it's a very good suggestion. And I'm, of course, looking for people who can help us make that happen. But I agree. I mean, I love the notion of its being gravity waves.
Great answer, John. Thank you for that. And thank you for your question, Remo. I think we just have maybe another minute or two. I want to inject my own question here. John, what kind of led you to start to have such a strong interest in these quantum fundamentals, if you will, this climate wave versus Copenhagen discussion? We'll just
two things. One is I studied physics in the 80s, and where we were, well, at my particular university, they sort of discouraged us from asking certain questions, which I found very anti-scientific. And so actually, I read recently something by Feynman where he says a scientist should have a good nose for bombast, and my bombastometer was just went off on as loud as the buzzer at the end of the talks, which we'll look forward to hearing, when I was listening to these discussions in my quantum mechanics course. So I sort of put it on the back burner, and I said went off and did fluid dynamics, but I'd always had an interest in quantum foundations. In fact, how did I first hear of Louis de Broglie? It turns out when I was 17, I was trying to decide what I wanted to study in university. My dad was trying to convince me to be a musician, despite the fact that I had no particular musical talent. So first, the conversation with my dad is like, Dad, what? To begin with, I'm not a good musician. Second of all, what kind of a father tries to talk his son out of going into science into music? And he goes, okay, fine. What kind of science? Like, oh, I think I'll do physics. And he goes, oh, have you heard of Louis de Broglie? What? So it turns out my father was a musician when he was younger. Then he became a French professor, and he did his PhD at the Sorbonne, and when on a Fulbright scholarship. And when he was, they had a ceremony greeting the new Fulbright students, and Louis de Broglie was speaking. And so my father, so I sort of learned about this later in life, and then I sort of read about de Broglie, and I've known, my father told me about him. And so I kind of liked his approach and his history. I find the history sort of scandalous. He, provided some of the cornerstones of quantum mechanics. The Einstein-de Broglie relation, P equals h bar k. Schrodinger's equation was derived to describe the pilot wave in de Broglie's pilot wave theory. And it was subsequent, the physical picture, which had sort of spawned, again, these cornerstones, was discarded in favor of nothing. And this is what motivated me. Because if there were people saying, no, quantum mechanics doesn't work like this, it works like this, I'm like, oh, okay. But they say, no, it doesn't work like that. It's impossible to understand. So that's why I do what I do.
I think that's a great answer to finish on. Thank you, John, for a great presentation, and thank you for fielding some of the questions. This was great stuff. So it's time for the next talk, 11:20. Next up, we have Dr. Setthivoine You from Holistic Space. He'll be talking to us about some work he's doing on a fusion propulsion concept. The title of his talk is The Development of a Physics-Based Model for a High-Powered Peristaltic Magnetic Nozzle. And he's in partnership with Caltech and University of Maryland, Baltimore County. Seth, you now have the con, sir.
Thank you very much, Sonny. I hope everyone can see my screen. Everything's fine. So sorry for the long title. It was a project title more than a presentation title. So my name is Setthivoine You, and I represent the project team here to talk about this new fusion concept. So the presentation will be in roughly two parts. The first part will be an introduction to this new fusion concept, why it's different from others, how it works, how it scales up, and kind of potential missions they could do that could be of interest. And then the second part will be really down into the details of the actual project. The work is actually part of a larger effort that includes other academic institutions and national labs to help further develop this fusion concept. And we're extremely grateful to the Limitless Space Institute for supporting this project, as well as the US Department of Energy, for helping us with some of this effort. So if you only want to remember one slide, it's this one, really. So we call this new concept the helicity drive for short. It's a pulsed magneto-inertial fusion system designed from the ground up really for space propulsion and power as you scale up. It exploits three key ideas, two really new ones and one really old one, I guess. We use magnetic plectonemes to confine the plasma. I'll describe them a little bit later. Magnetic reconnection heating to preheat the plasma to high temperatures before doing magnetic compression in a peristaltic fashion to raise the energy density to fusion conditions. And the key result really is that we have a scalable triple product, which scales with a new parameter n, which is the number of plasma sources, which effectively acts as a new control knob, in addition to other fusion concepts that magnetic fusion concepts that use plasma current or magnetic field or plasma size, and for inertial fusion concepts, compression ratio as control knobs. This one is a new one. The number of original sources is another one, and it scales quite nicely. Why is that useful? One thing is you could effectively compensate for uncertainties in confinement time. It's one of the major issues of any fusion concept is how to confine the heat. And that's really hard to understand and how to scale up. But if we have this extra control knob that is reasonably easy to change, we should be able to compensate at least a little bit for variances in confinement time. The other useful engineering input is that you can spread the necessary input energy to generate fusion, the minimum energy, over n guns, rather than just over one single gun. And as you want to increase performance, you increase the energy density of a single gun. You can think of a Z-pinch, for example, and so on. The other usefulness is that we have a development path that is, we call it analogous to cylinders of car engines. So instead of increase the size of a single cylinder engine to try and increase performance, we can just go to a twin cylinder, a 3-cylinder, 4-cylinder, the V8 and so on in the future. So that's the fundamental key result. So the big picture, let's just talk a little bit about the philosophy about this novel fusion concept. The key philosophy behind this concept is that even if we manage to achieve modest net gain, break even, we believe that it's viable already for space propulsion. Pushing a spacecraft is easier than generating net power. The minimum viable performance we find, and I'll describe the scaling laws, is actually quite similar to state-of-the-art nuclear electric propulsion. And the key idea is that really you can simplify the scalability, and that will allow us to rapidly test the idea at very, very small scale with modest means, and then ramp up. And then not only ramp up to net gain and so on, but in principle, we should all the way ramp up to the huge, large and extra large sizes for power plants and so on. So on the right is the key plot. It's really a comparison with just general rocket propulsion. The specific power as a function of the specific impulse. We know that chemical propulsion is very mature, has low specific impulse, and very high power. So the space shuttle, the Starship, Raptor engines, and so on are on the top left of the curve. It's extremely useful, but we know that it's very limited. There's a big trend now to try and double the performance effectively by going to nuclear thermal propulsion, which is very nice, but we know that it's still going to be limited. On the other end of the scale, we have electric propulsion with ion thrusters or Hall thrusters, where you take some electrical power source and couple it to a plasma thruster that tries to accelerate a cold plasma as efficiently as possible without any heating. You have much better fuel efficiency because you have higher specific impulse, which is great, but you're primarily limited by the onboard available in-space power. So with solar electric, the largest solar electric propulsion mission at the moment is Bepi Colombo on its way to Mercury. It's 18 kilowatt solar electric mission that is using these kinetic T6 ion thrusters to fly there. State-of-the-art concepts using nuclear electric like GMO and Cassibry and so on assume an order of magnitude increase in electrical power available in space. And then when you couple these heavy fission reactors to these arrays of ion or Hall thrusters, you get interesting missions orbiting the icy moons of Jupiter, for example. Now, we know that fusion is really, really useful. It would be on the top right, and that's what opens up the whole solar system. The traditional way of doing fusion using magnetic fusion, I'll just talk for direct fusion propulsion at the moment, is steady state and self-sustained. So you get really nice performance on the top right of your plot, whether it's a spherical tokamak or a spheromak with gigawatts of power, it's all very attractive if you could get there. The thing with magneto-inertial fusion is that ours is direct, pulsed, is that we can actually scale down to the green area, which is closer to the standard nuclear electric propulsion, where effectively we have a small engine that doesn't generate any power, but only uses fusion to exhaust and increase the thrust, and the ability to scale up when you add some recirculation systems until you completely self-sustain. So let's compare it with other fusion concepts. Now, we believe that magneto-inertial fusion is a nice approach to try to beat the Lawson criterion. In magnetic confinement fusion, the only way to really increase your confinement time because you have such low density is to increase the size of the machine. That's effectively the main control now. Most of the heating is lost because the heating time is much longer than the energy confinement time. In inertial confinement fusion, the heating compression time is extremely fast, much shorter than the disassembly time, but the energy input is extremely inefficient and it has to be in the petawatt scales. So the only way to really increase density is to increase the driver power. Magneto-inertial fusion is nice because it's in the middle. It's a Goldilocks approach where your heating compression time is roughly on the order of the energy confinement time. So in principle, it should be a more efficient use of input energy. The density is the y-axis in these three plots. Also controls effectively the size and mass of the fusion reactor, and therefore also the cost. Being at this intermediate density reduces the reactor size and cost. It reduces the magnet size and cost. It's more efficient driving, and you decouple power from size with pulse frequency, so you can control yield and pulse frequency separately. So in principle, it should be more compact and economical, and therefore easier to launch into space. Now, fusion propulsion concepts, there's been many, and this plot here is adapted from Jason's old paper. I should update it with more data from the more recent fusion concepts. But the general trend is this: you have, again, in terms of density, so being in the middle is good because you're supposed to be lighter and more energy efficient. On the left, you have the steady state magnetic fusion concepts. On the right, you would have the inertial confinement fusion concept. And then the y-axis is your specific power. Now, generally, if you do your back of the envelope propulsion calculations, you want a specific power of the order of 1 to 10 to really open up the solar system for space travel. But the key point is this: the fusion propulsion concept in steady state generally are pretty massive. So the size of the circle represents roughly the mass of the fusion concept. It's on the order of the thousands of tons that you have to launch. And the specific thrust power is of the order of 1 to 10 kilowatts per kilogram. So it's great if you could launch thousands of tons into space, a reactor. The pulsed magneto-inertial fusion concepts are in the middle. It's pretty nice, but some of them are pretty massive as well. Our concepts are generally lighter. They appear to be smaller and lighter, but also a key point is that the pulse frequency that we assume, if it's fully self-sustained and everything, we assume a modest 1 hertz. The other fusion, inertial fusion, magnetoinertial fusion pulse concept assume 10 hertz, 20 hertz, or 100 hertz of pulse rates to be able to have very high powers. So if you divide effectively, assuming everything else remains equal, if you divide by 100, divide by 10, or divide by 20, the specific thrust power drops. Now the green and red small engines, have much lower pulse rate because we assume here we only have 100 kilowatt electric input auxiliary power to do the fusion conditions. So it's not sufficient to generate full energy, so pulse rate is much lower. However, even at those low pulse rates, you have specific thrust powers which are, similar to nuclear electric propulsion with that scalability up to the blue states. So how does the scaling work, the scaling of this fusion performance? So the green, red, and blue is really the three classes of engine. The green small engines is what we call the fusion augmented electric propulsion, FAEP, where there's just no power. It's literally a fusion thruster, if you want. It's a fusion augmented thruster. Say, for example, if you assume 100 kilowatt electric input, you get 50s of kilowatt thrust of propulsion, which isn't great, but if we can fly something like that, it would be the first fusion propulsion system in space. But the concept and geometry, just by increasing the number of guns, could go up, to the red ones. For example, when you add a power conversion system to supplement the auxiliary input, then you can even get more thrust out than the electrical energy put in, thanks to the nuclear reaction. And then, of course, the standard fusion drives, where the power conversion is sufficient for 100% recirculation, and the excess energy can even be sent to the grid for onboard power. So the plot in the middle is literally that. This are results of our scaling calculations, very basic back of the envelope scaling calculations with the assumptions on the right column. And you get the fusion power scaling literally as a function of the number of guns, assuming everything else remains equal. So the guns remain exactly the same. All you do is add more, and they merge all together into a single plasma object. And then you add recirculation or not, and so on. The dashed lines are the propulsive power. The solid lines are the fusion power. So it's propulsive power is a fraction of the power conversion. Compared to some other quite efficient magnetoinertial fusion concepts, for example, the pulse fission fusion hybrid, we use non-radioactive fuel, so we don't use uranium and so on. Our pulse rate is very conservative because we don't have anything material. Everything's magnetic and plasma. It's much easier, so there's no material liners like liquid liners or solid liners or plasma liners. We have a reduced compression ratio, so I'll explain that in a second, because we do the preheating using magnetic reconnection. And because we have multiple guns, the gun energy density per gun, and because we don't compress as much as, for example, the shear flow Z-pinch, in principle, we have room to grow, room to scale. And then compared to some other magnetoinertial fusion concepts that have material liners that are very difficult to make perfectly symmetric and so on, are very cold compared to very hot plasma and very hard to get high pulse rates. We can talk about the assumptions. They're conservative. There's some pragmatic ones, and there's some optimistic assumptions, like any concept. What can these engines do? Okay, so three different possible engines. What we believe is the nearer term, if we could scale quickly with our experimental results and so on, is really the focus of what we want to do, would be this minimum viable tech level. Build devices on Earth, test them, test the ideas, see if the triple product scales. If we do get net gain, then configure it to be autonomous and fly a demo flight just to prove that it can be done. These are the mission level figures of merit, assuming we have a 10 kilowatt electric input or 100 kilowatt electric input. Can we move something from LEO to Lagrangian 4 or 5 with a delta V of about 4 kilometers per second? What kind of initial mass we can launch this on a 1 Falcon 9, for example, and just test the idea as a very, very short, simple mission tech demo. The really interesting missions become interesting once you add some recirculation and really improve the performance. That's the medium red scale, medium column. Here, we're working on it. We're not claiming this is really the best way of doing it, but we're interested in seeing whether a reasonably efficient, reasonably useful fusion propulsion system could act as a cislunar freight cycler for very heavy cargo. So, for example, if you want to take 100 tons to lunar orbit, using chemical propulsion, you would need 190 tons of fuel, which means that you would need to launch 4 Falcon Heavy just to refuel at a cost of about $360 million if it costs $90 million per launch. And that's just for a one-way trip. Maybe nuclear thermal propulsion, can be a little bit better. But the helicity drive, if we could do this with these numbers, could complete the mission 7 times more economically because we have much less. We only need 9 tons of propellant. We launched a Falcon 9 instead, so it costs $50 million for refueling. And then, of course, if you go back and forth and cycle, you compound the savings. So that's something which is interesting. It's obviously based on many assumptions. And of course, if you scale to the full fusion drives and so on, we fall in the same category as other fusion concepts. We open up the whole solar system. We can fly to 1,000 AU and start trying to observe exoplanets 100 light years away. We can do planetary defense with scrambling payloads, heavy payloads to delta Vs of 50 kilometers per second and interstellar objects, even do sample returns from that. And then this is probably, I think it was mentioned before, Jason mentioned before that fusion is a little bit at the limit for interstellar missions, but if we take our best possible, most efficient fusion engine with deuterium helium-3 and you could accelerate nonstop for 100 years, you would actually reach Proxima Centauri. Okay, so how does this concept work? It's a 4-stroke engine, so we form these plectronemic jets at the beginning. Now, each of these jets, the plasma, magnetized plasmas, they have a certain density, a certain temperature, a certain magnetic field, a certain radius. Now, you might have guessed it in the name. It has a certain amount of helicity inside it, which we characterize by lambda, a certain length, and a certain confinement time. You merge n of these together in step 2, and through reconnection heating, the end object, the end plasma, will have a certain density, a certain temperature, a certain magnetic field, and so on. And you can predict, you can have a back-and-arrow calculation through helicity conservation and energy conservation, how much of the magnetic field, initial magnetic field content was converted to heat, and ion heating. So we preheat this plasma. Then you do a compression using peristaltic magnetic compression. So there's a traveling magnetic field that will implode, and I'll describe that in the second part of this project. Characterized by a given compression ratio and the actual geometric details characterized by the constant C, which will then raise the density, temperature, magnetic field, dimensions, and so on to the final state 3. Then to generate thrust and cool down the actual fusion products, once you get fusion, you would mix it with an inert propellant and cool it down, increase the mass, the m dot, to control the thrust. And then the way you would do it would, at constant fusion power, will bracket, if you want, the lowest ISP and the highest ISP, the minimum thrust and the maximum thrust. The 3 plots on the right is effectively the scaling that we get out of it, the triple product as a function of the number of objects you merge. In our scaling calculations, we assume a conservative Bohm scaling. And when you work out the equations, as you increase the number of objects that you merge, your triple product actually goes up, which is part of the nice scaling. But of course, at some point you hit the burn through limit where you burn all your particles. So that'd be the maximum peak performance fusion triple product that you could get after merging X number of objects. Another interesting result from this, because of the preheating, so that's the second plot on the right, is that we start at a higher triple product value after the merging reconnection. So you don't need as much compression to reach net gain compared to, for example, the gray box, gray shaded area, which is the shear flow Z pinch. They're scaling, they will take a cold plasma at a few EV and then need to compress by, say, 30,000 or so to reach a net gain. The slope of the curve in a shear flow Z-pinch, the steeper slope is their assumption, optimistic assumption of confinement time that scales as the flow through time of a long, 1 meter long Z-pinch. Then I basically did the same derivation, but then the shallower slope is assuming a Bohm confinement time. That's just to be able to compare with our Bohm confinement time scaling. So the thinner curves, numbered 3.0, 5.4, 10, and 100, is effectively the compression scheme. It's the decision on how you actually do the magnetic compression, and I'll talk about that in detail, to control the slope and to be able to reach the fusion condition. The bottom plot is really to show that, of course, we want to reach the self-heating regime and so on. But one thing that's interesting with this, because we control the preheating independently from the compression compared to every other concept, there is the potential of reaching the self-heating regime, or at least generating alpha heating, before you reach net gain. Basically, you generate enough fusion reactions to be able to compensate, for example, for energy loss or cooling of the ions with respect to electrons and so on. That remains an operational node that can be thought of in the future. The physics basis behind all this. So the magnetic confinement configuration, we call it a plectoneme. It's, for those that know, it's a Taylor state. It's very related to a spheromat. But it's not a torus. It's actually twisted into a double helix. So you can take your rubber band and then imagine it's twisted and stuffed inside a cylinder, a flux-conserving cylinder. We've observed this in 2 experiments, the Swarthmore Spheromat experiment and the Mochi experiment at the University of Washington and Swarthmore College. They have some really interesting properties. They're Taylor states. They have nested flux surfaces. They're relaxed configurations. They're compact and they're very far from walls. We don't need close-fitting walls to stabilize them or center columns or anything like that. They're self-stable. Experimentally, we've observed them to be high beta, even though from a theoretical point of view, Taylor states are 0 beta, but it should go somewhere in between 0 and 1 in principle. One of the reasons why we need walls, close-fitting walls or center columns and so on to be able to stabilize to stabilize toruses is because they're tilt unstable. In our case, they've already tilted and they're very stable, so we don't need close-fitting walls. They do have rotational transform. And one thing which is interesting compared to a donut is that the Q factor for confinement is the number of toroidal turns per colloidal turns, or vice versa, depending if you're a stat racer. And that ratio is important for confinement and stability. But if you take that torus and then you stretch it like pasta and then twist it, then basically the number of colloidal turns and toroidal turns is equivalent to this long axial aspect ratio, and then the number of wave numbers along the z direction. So there's a potential of being able to control, at least geometrically, the equivalent Q factor with the aspect ratio. The second ingredient is reconnection heating. It's a very natural phenomenon observed in space when you take 2 magnetized objects under the right conditions. When you push them together, part of the magnetic field will dissipate, magnetic energy will dissipate and convert it into heat. The thing that is really interesting, and we've observed in the laboratory across many experiments, that's a data set you see in the plot there, is that it's very high power heating. It's extremely efficient. 90% of the dissipated magnetic energy goes directly to the ions, not to the electrons. That's very useful for fusion. It's internal to the plasma. It doesn't come from the outside, which is very good for heating. And there's no need for perfect geometry for implosion and things like that. It's very robust. The animation here is some MHD simulations where we start doing of taking multiple of these jets and merging them together. The SSX experiment has managed to merge multiple plectonemes together and observe some ion heating. Then there's magnetic compression. So you take this preheated hot plasma and then you stuff it inside an external magnetic field that has a mirror-like shape, if you want, but it's traveling with the plasma and then squeezing it. So it's like toothpaste squeezing your plasma. We've made these in the laboratory decades ago on very small tabletops. The advantage is there's no moving parts, so you can have really high speeds, and there's no cold liquid plasma material liners to control. It's constant energy, which is much more efficient than increasing the energy of coils, and it's reasonably simplified symmetry. Now, it's a new concept, so of course there are a lot of uncertainties in physics, engineering, and of course business and geopolitical. I mean, we dream of a spacefaring civilization, but you know, in this talk, I'll talk about the physics and the compression scaling, but we do address all the other items bit by bit and slowly. When we mean by design for fusion propulsion is that all these challenges are interdependent and will inform, for example, even the physics. There are some physics or some engineering solutions that we may discard, for example, because it would not fit, for example, cost scaling or and so on and so on. The timeline at the bottom shows where we are. We're based on all the experimental results in the past. We're gearing up to build a new experiment, which we call Eclair, and then hopefully be able to scale up all the way up to the Higgs. So now we're at the second part of the talk, and that was the general context. And this project really is to study the magnetic nozzle. And the scaling calculations that we did assumed a certain gun specification and a certain compression ratio, which are the free parameters. You can see the triple product scaling equation down here. The final triple product at peak compression, state 3, scales from the starting gun triple product with the number of guns, the compression ratio, the compression scheme C, and the parameterized reconnection specifications, which are the flux conserving volume change between state 1 and state 2. So those are the experimental knobs that we can control. And clearly, if you increase the compression ratio, you have better triple product, but you could also have lower compression ratio and a larger number of guns, you see. So that's part of the experimental control knobs that we would like to be able to use. So then the figures of merit at the top are the examples, just to show if you had a density compression ratio of 500, you know, and you have a number of guns between 51 and 100, you could have these specific powers between 3 and 7. But if you have a compression ratio of only 60, you need hundreds and hundreds of guns to achieve fusion. But you have a much wider range of possible specific powers precisely because of the larger number of guns. Now, of course, there is assumed a lot of fixed, you know, basic parameters, initial plasma parameters, gun specs, reconnection parameters, and so on. It's really just to show the scaling. And of course, we need much more realistic considerations for the coil system. Mutual inductance, dispersion, resistivity, coils, and so on and so on. Of course, we want to couple to the plasma itself and then the back reaction on the coils. So that's the goal of one of the goals of the experiment we want to build, but also the simulations we're working in. And of course, there are some engineering constraints. So how does a magnetic compression system work? It's an old paper by Paul Bellin, who came up with the idea. He developed this theory of having tapered arrangement of coils, and then when you would send a double current pulse into it, and the coils are connected together with capacitors. So the whole thing looks like a standard transmission line, just with varying inductances. You could also do the same thing with varying capacitances and straight coils. But basically, by having these varying inductances and in this connected transmission line geometry, the current pulse that travels through energy conservation will effectively slow down and steepen. And then the second pulse coming into it will slam into the back of this slowing down front pulse and steepen as well. So in the frame of the traveling wave, you effectively have an imploding magnetic mirror field. And the important advantage compared to other concepts, like increasing current coils in the magnetic mirror, is that you can do this at constant energy. It's much more efficient than just increasing the coil current. A heuristic way of understanding this is that if you increase the coil current, you're effectively creating new magnetic field lines to be able to compress to a smaller radius, rather than just using the taper of the coils itself. The other thing, because it's slowing down, more time is spent in the peak compressed state than in the initial cold state, which is very useful for fusion concept. So this theory was developed and demonstrated on a small tabletop setup that was about 50 centimeters long and a few hundred joules of energy. And the goal is that we really need kilojoules of system for this experiment, nuclear experiment we want to build. And then we want to scale up eventually, probably to megajoule systems according to our back-of-the-envelope calculation for the full fusion net gains and propulsion systems. And of course, we want to couple to the plasma. Sorry for the dense slides, but basically on the left column is the theory and the free parameters that control the theory and the results of this, the theoretical scaling. There are 4 parameters. It's the number of coils you want in your nozzle system, the radius of the coils and how they taper and vary, the number of turns in each of these coils, which controls the inductance, and then the compression scheme, which we parameterize by a constant C. And depending on what you want, you have a separate shape and geometry and spacing between the coils. If you have a constant flux compression, for example, C would be equal to 4. If you have a constant geometry, that means the radial compression ratio is equal to the axial compression ratio. So the cylindrical volume implodes with the same aspect ratio. You can choose C equal 3, and so on and so on. In fact, in the calculations, we can actually use exactly the same formalism to compare with the Z-pinch compression just by setting C equal to 2, and we get the exact same end result. It's a different compression system, but it's not external, it's internal. So from these 4 free parameters, you get the position and separation of the coils. Delta is the separation between the coils. And then from that WKB scaling, you get the magnetic field ratio, the mirror length ratio, and the compression volume. And that's what we used for all our scaling, and figures of merit for the missions. Clearly, this is just a WKB scaling. So when we want to build this experiment, we have the conceptual design, and then at the start of the project, we had some ideas as to what we wanted to do. Because our scaling calculations use a constant exponent C of 5.45, we decided, okay, let's keep that. So that means if we build this experiment, we can test with, 2 guns, 3 guns, 4 guns, and that's already starting us on this scaling curve. So we fixed that. We wanted a density compression ratio just to demonstrate we can compress maybe 2 orders of magnitude up from the density in Mochi. So that was the initial aim, but it turns out once we started doing some iterative calculations and simulations, the voltages and currents would be way too high. So we're reducing down to about a factor of 40 or so. And then the temperature ratio would be, of the order of 10, hopefully. So that's what we're thinking of. And then we're fixing the geometry as we are building the guns and fine-tuning the design of the guns and the angles and the vacuum chamber and so on. So for those interested, let me walk you through this design formalism. It's slowly. It's not complicated. Sorry, it's dense. So this is what we do. We select the compression ratio, the compression scheme, the density ratio we want, the magnetic field ratio we want, the number of coils, the shape. The color coding, green is that the numbers that we've roughly settled on. Yellow, we're still iterating and designing and to decide what the actual numbers are going to be. And then red are your N constraints or potential issues that we have to think about and reiterate. So once you choose all that and you've chosen the inlet geometry, so the distance of the coil from the guns and then the separation from the first coils, which determines the overall length, if you want, of your nozzle, you get out the vectors of all the coil radiuses, the number of turns, the separation between the coils. From that, you can get the circuit characteristics, the LC time, and then the velocity of the waves that travel through it, which you can then compare to the plasma characteristics. These plasma jets that travel, so in the experiments, we know at what speed they travel, roughly half to 80% of the Alvin velocity. And we're confirming that with the NHD simulations. So, it also gives us an idea of what kind of capacity we'll need. So at the moment, 10 microfarad, giving us the peak voltages, peak currents, and the stored energy. So this is the 9-10 kilojoules of energy that we need to store. And then in the future, because we still eye this propulsion system, we want to be able to get the scaling for the total mass of this magnetic nozzle, because that will be part of the fusion engine and the specific power overall. We need to have a scaling law for that. So we're considering that too. That gives us the peak magnetic field and the magnetic field ratio. We can also solve for the dynamics. Now we solve for the time-dependent current and time-dependent voltage in this matrix equation, because we now want to take into account the mutual inductances between the coil. That's
3 minutes.
Wow. Okay. Time flies when you're having fun. Sorry, guys.
That's all right. Good stuff.
So you can solve these equations and you get the dynamics of the magnetic field, from which you can actually get the peak field and so on and see whether it fits with your end design. The inputs to that would be the input pulse, the shape of the pulse, and which will inform how we're going to do it in real with the pulse forming network. The results of the simulations, we're going to couple it, and we're going to couple it to the plasma simulations that we're doing with Los Alamos. And then the geometry, we've already started testing the first coil, just to learn how to cut the coils and test it and stress test it, and so on. And that will actually inform some of the details in the vacuum chamber design and so on and so on. So we're iterating through that. This slide was to talk about some of the realistic effects that we have to take into account, particularly the mutual inductance between the coils that effectively reduces the peak field from the WKB theory. And sometimes it can be quite drastic. You can see in the second row here that the WKB expected peak field should be about 1.6 Tesla, for example, for our specs. But depending on the input pulse we get, it can be a factor of half or less from that. The dispersion, the finite dispersion of the transmission line is also another issue because it further reduces the peak field as well, although we have ways to mitigate that or maybe increase the voltage. And that just explains some of the details that we have to think about. So basically, if we wanted a compression ratio of 40 and a magnetic compression ratio of 6, 10 kilovolts, so we need to work with all these constraints. Maybe go to higher voltages. I'm almost finished, but we've already started building the hardware and designing, so the coils are looking much more realistic, and cutting them, and even details like stress calculations and cutting washers between these bitter plates and so on, and how to mount them through the chamber is ongoing and will be ongoing over the summer. This is just hand waving. It's coupling all these pictures together into the various simulations and so on, just to show roughly how these jets can go through the nozzle in these various time steps and how we can use it. We're halfway through. We're roughly on time according to plan, and what remains to do is all that verification and validation, finalize the design, interface with the simulations, and then really get the scaling laws. This is the team. So the Caltech team are on the left, and then the UMBC team, including the senior undergrads that are helping us build some of the coils on the right. So that's the summary. Thank you very much for your time. And I'm a big fan of Star Trek, so I was very happy to get that.
Awesome. Great job, Sid. If you could stop sharing your screen, that'd be great. It was really neat to see all the pictures of the students involved, and I know there's students involved in all of this process, right? So I'm just very thankful to see that type of engagement. That's really good. Thank you, Seth, for your talk. Thoroughly enjoyed it. We have a few questions in the chat, the Q&A chat window. But before we go to those, just to open it up to the panel, anybody have any quick questions from the panelists?
Yeah, I have a two brief comments and one question. Can you hear me okay?
Yes, I can.
So I wouldn't say I completely fully understood it all. First comment is, have you heard of Project Icarus Firefly concept?
Which one?
Project Icarus Firefly. It's a concept developed by Robert Freeland, and it's been published in a couple of JBIS papers. If you drop me an email, I can send you a link to the papers. But the concept is very similar. It's and it was published sort of 5-6 years ago, but there's 2 papers published on it, and it's a Z-pinch driven inertial fusion system, but it's got very many similar ideas to your concept, so it's worth looking at it. Just a comment about inertial fusion. One of the things I like about inertial fusion, you're right, that obviously it is dependent upon the laser power, but it's not entirely. I mean, inertial fusion is, you're really racing between the losses and the gains, right? So you're trying to compress up to your compression ratio to get to your alpha particle deposition, but you're losing energy at the same time. And one of the problems of some of these schemes is you're depositing electrons, which preheats the fuel. And so what was realized was that there's ways of getting around that, which is to cleverly design different capsules. And so that takes you away from being just linearly dependent upon the laser power. So for example, there's a concept called shock ignition, which has these very thick laser shells. I think I mentioned that in my last talk, where the electrons are deposited actually into the shell itself. And this amplifies the power. And as a result, for a typical NIF capsule, the actual power goes something like, the energy that comes out of the capsule goes something like 100th times the laser power to power of a half. So there's lots of different schemes you can play around with, like fast ignition, short pulse lasers, and long pulse, separating the ignition from the hydrodynamic phase, which allows you to play around with that. The other point I wanted to make was, you mentioned Lawson criteria, which is obviously fundamental to all of this fusion stuff. And you know, inertial fusion is really, it's going for that high number density, also that high temperature, and confining for a very short time. But one of the beautiful things about that is, of course, the fusion production rate is dependent upon the temperature. So if you can compress up to high compression ratio, you get high temperature, which means you can get high fusion rate, which means you can get a high gain if you can inertially confine it for long enough. So I'm wondering if your concept might be limited in terms of the gain that it can achieve, because you're not going to such high compression ratios, and therefore the temperature might not be as high.
Correct. Yes, I mean, because it's magneto-inertial fusion, we are orders of magnitude lower density than inertial confinement fusion. So we're trying to hit that sweet spot of we have reasonable gain, reasonable yield, if you want, in the language of ICF, but a reasonably high repetition rate, of course, compared to that. But we're still much more modest compared to other magneto-inertial fusion concepts. We don't need tens of 20, 50 hertz, for example. So
yeah, but I'm interested in the outer bounds of the performance, what you can actually do if you take it to its limit. And by the way, you could add stages onto your vehicle to push that, that performance up even further.
Yeah, at the full performance, with reasonably efficient subsystems and everything, we get 68 kilowatts per kilogram, or 1 hertz. If we do at 10 hertz, we get 680 kilowatts per kilogram. So yes, in principle, we could. With deuterium helium-3 at reasonably 10 to the 27 particles per meter cube type densities. So it's reasonable. But we're really concentrating on the closest triple product gains rather than the furthest one, because the acidity grows, of course, the further. And we really want to focus as quickly as possible, even just seeing whether we can get this compression to work together. The many details of timing and coupling and efficiency in the coupling itself between the plasma and the coils and all these things. And even the reconnection process as well. There's uncertainties. I can talk about hours for this, but like the beta ratio, for example, we've assumed ideal beta ratios, but what are the real beta limits that we will be able to attend and attain, and so on and so on. Absolutely.
Thanks, Seth. Thanks, Kelvin. I've got a couple questions in the Q&A panel here. Let me catch one of those. We got one from John Scott. He says, you mix the plasma with the propellant. How efficient is this process of energy transfer? How much space is required, and what happens to the lost heat? So he's actually getting a 3-for-1 there, but just if you can answer that in a minute and a half or less.
Yeah, so that is one study effort that we're starting, and we would like to work on. It's based on past experiments where we shot plasma jets at neutral gas clouds, and also some of the work at Los Alamos, for example, the plasma magneto liner, PNGIIF, sorry for the acronyms. Injection of plasma guns into a background plasma, for example. So that interaction that we've seen shows that at least the momentum transfer is extremely efficient, whether it's viscous or some other mechanism, at least with neutral gases. Now, in terms of the energy transfer, we're not 100% sure how efficient that can be. In our basic overall calculations, we followed the AIAA recommended design practices for fusion propulsion systems. It says if you don't know, just choose 0.7. That's what we did, and we're setting up a project to study exactly that in more detail. Once we have the experiment, the exhaust part, so that's step 4 that I didn't mention so much, is exactly where we're going to look at the energy and momentum transfer there.
Got I guess more of an informational question from Creon Levitt. Is there a conference for magneto-inertial fusion approaches? This, I guess, is to all the fusion folks. We got 4 you guys. So what's your favorite fusion conference?
Well, usually the best one is always the APS DPP, Division of Plasma Physics annual conference, where basically almost all the fusion concepts get together, and you can see all the posters. The only downside of that meeting is so big, there's so many parallel sessions, you don't get to see everything.
Right, and I think we've got one of the attendees has a raised hand. I'm going to see if I can't allow them to talk. Dylan, do I just push the allow to talk button? Ken Louis got a question.
Yeah, that's right. Yeah, I think if you just click the allow to talk button, that will work.
Okay, all right. So Ken Louis, I'm going to click allow to talk. I think you are muted or something like that, so you may need to unmute before you talk. Ken, are you still there?
I think, is it Ken Louis?
Yeah, Ken Louis.
Oh, he's muted, I think.
Yeah, Ken Louis, you're muted if you're talking. We cannot hear you. Ken, you're still muted. Okay, well, while he's trying to get that sorted out, I'll grab another question over here in the window. This simple question: where is the ignition point in the engine? Set.
It's at the throat. Effectively, when you do the coil, as it compresses, at some point there'll be a Z position where the triple product is beyond the Lawson criterion, Lawson minimum. At that point, it starts igniting and burning. Okay. Now, you can work for a fusion reactor. Then at that point, you can start choosing the length of the burn. You know, burn as much as you want or as little as you want, depending on the configuration you want. So that's another geometric flexibility. This plasma traveling can burn itself.
Okay, cool, very cool. So I'll, I guess Ken was not able to get his microphone unmuted, so I'll finish my own question here, and this will wrap us up for the day. So Seth, I mean, obviously a strong interest in physics and so forth, but you know, why fusion? What draws you to this specific field? Why do you want to go do things in space like this?
I've always been interested in science as a kid and space, and you know, wanting to be an astronaut like every kid. But I grew up in France, and I was subscribed to the French popular science magazine Science et Vie. And I remember I was 13, 14. They had an article on fusion, jet, actually, the jet tokamak experiment in the UK, in Culham. And at the end of that article, they were talking about how you could use fusion for space and open up the whole solar system. So that's when my visions of Star Wars, Star Trek, and so on said, oh, it could actually happen. And 10 years later, I did my PhD in Cullen on the mass tokamak. And then I came over to the US and started studying non-tokamak fusion. And that really piqued my interest because I knew from the beginning tokamaks were great. They're fantastic, but they would never fly. So I wanted to find a more compact fusion. So then I started searching, and I went to University of Tokyo and University of Washington and so on, and started looking at other fusion concepts. But every single fusion concept had its issue. So I always wanted to find a fusion concept that would try to reduce some of the limitations of the other ones. And it needed the key ingredient. It needed a key stable magnetic confinement system, and it was the plectinine. It needed that discovery because everything else is known. But initially, my idea was always to merge multiple toruses, and many people have done that. But there's big issues with that. Once you have these plectinines, you could really go for it. So one day, as an astronaut, we'll have our own rockets and fly around the solar system.
I love that. From your mouth to God's ears. That'd be a great outcome one day. Yeah, thanks, Seth, for sharing that personal side of things. So I think that wraps us up for today. We've had a good, productive day, going through some great talks. I thoroughly have enjoyed every single one of these talks. Let me bring up the agenda for tomorrow real quick, just to give everybody a preview. I'm going to share my screen. Some of the stuff out of the way. I lost my mouse. Uh-oh, where'd my mouse go? I got 3 screens. All right, there we go. So this is the agenda for tomorrow. We're going to be, we'll kick off the day with some really inspirational words and charts from Space Commodore, Space Commodore Pete Warden for Breakthrough Initiatives, talking a little bit about some of the things, the interstellar musings and thoughts that he has. So we're excited to have him kick off our day for tomorrow. We'll have Professor Richard Norty from Delft University of Technology. Will talk to us about some of the relativistic solar sail work that he's doing. Charles Chase from Unlab, along with Yuval Dagan from Technion, will talk a little bit about asymmetric potential vacuum fluctuation forces. Professor Remo Garantini of University of Bergamo will talk to us about traversable wormholes. Kevin Long will be talking to us about some inertial confinement fusion work that he's been doing in terms of some very detailed code that he's developing for us. And then Professor Ray Sedgwick will finish up the day from University of Maryland. Will finish up the day with his centrifugal confinement direct drive fusion propulsion talk. So I hope everybody gets a chance to join us tomorrow. One thing I did want to highlight about today is I tried to write down some memorable quotes. It's always interesting when you get a bunch of smart people together, the things that we say that are just absolutely interesting and I think memorable, if you will. I think Phil Lubin said something that I wrote down. Autonomous driving on Earth is nice, but eventually we will want autonomous spaceships. So I thought that was a pretty cute little saying from Phil. So thank you for that. And then John, I think you definitely said something that I probably would like to put on a coffee cup. We did what De Broglie would have done if he had MATLAB. I thought that was fantastic. That was definitely the quote that topped my list for today. So, all right. I guess with that, thanks everybody for joining us today. Thoroughly enjoyed it. We'll get started tomorrow at 8 o'clock and then finish up probably around a little after 1 o'clock in the afternoon. These are, of course, Central Daylight Time. So special thanks to the folks that are on the West Coast supporting. So they had to get up really, really early. And then the folks that are all the way far to the east in Israel, I know it's late in the evening for you, Yuval. So thank you for continuing to stay up past your bedtime. So looking forward to tomorrow. Thanks, everybody. I'm going to bring down the loops now, and so the YouTube will shut down, and then the Zoom webinar will shut down right after that. So thank you, everybody, and have a good day.
Thanks.
Bye. Bye there.
See you guys.
Thanks, everybody.